4.6 billion years ago, there was no sun, no Earth, not even planets, only a vast cloud of gas and dust drifting through space. Then gravity began its work. What started as scattered particles collapsed, ignited, and transformed into the system of worlds we now call home. Understanding this process isn't just history. It explains why Earth exists at all and why life had a chance to begin. The iron circulating through your bloodstream at this very moment was forged inside a dying star more massive than our Sun. That star lived fast, burned bright, and died violently in a supernova explosion that scattered its nuclear-forged elements across light years of space. The calcium strengthening your bones originated in the collision of two neutron stars, an event so energetic it created gravitational waves that rippled through space-time itself. The oxygen sustaining every breath you take was manufactured in stellar cores operating at temperatures exceeding 100 million degrees Celsius. These elements did not simply drift through space waiting to become part of you. They underwent a 4.5 billion year journey through one of the universe's most spectacular construction projects, the formation of our solar system. This was not a gentle, gradual assembly, but a violent, chaotic process involving temperatures hot enough to vaporize rock, impacts powerful enough to shatter worlds, and gravitational forces capable of hurling planet-sized objects across the solar system like cosmic billiard balls. Consider the precision required for this cosmic construction project. If the initial cloud of gas and dust had been rotating just 10% faster, centrifugal forces would have prevented planets from forming altogether. If the heavy elements forged by previous generations of stars had been distributed slightly differently, rocky planets like Earth might never have accreted enough solid material to reach planetary size. If the timing of planetary migration had been altered by just a few 100,000 years, Jupiter might have spiraled into the Sun, taking the entire inner solar system with it. The formation of our solar system required the coordination of physics operating across scales from subatomic to galactic. Electromagnetic forces caused dust grains smaller than bacteria to stick together. Gravity amplified these tiny aggregations into asteroid-sized planetesimals. Conservation of angular momentum transformed a slowly rotating cloud into a rapidly spinning disk. Thermodynamics created temperature gradients that determined which materials could condense at different distances from the forming Sun. Fluid dynamics generated turbulence that mixed and concentrated solid particles. Nuclear physics ignited our star and established the energy source that would drive atmospheric evolution on every planet. What makes this story particularly remarkable is that we can now read the history of these events in exquisite detail. The composition of meteorites reveals the temperature and pressure conditions present in different regions of the early solar system. Crater counts on planetary surfaces record the timing and intensity of bombardment episodes. Isotopic ratios in lunar samples provide timestamps for when the Moon formed through a giant impact. The orbital architecture of planets preserves evidence of their migration through gravitational interactions. Modern astronomy has revealed that planetary systems are common throughout our galaxy. The Kepler Space Telescope discovered thousands of exoplanets orbiting other stars, revealing an astonishing diversity of planetary architectures. Some systems contain super-Earths larger than any rocky planet in our solar system. Others feature hot Jupiters orbiting closer to their stars than Mercury orbits our Sun. Many systems show evidence of violent dynamical evolution that scattered planets into highly eccentric orbits or ejected them from their systems entirely. This diversity makes our solar system's particular configuration appear almost miraculous. We possess 4 terrestrial planets with thin atmospheres, 4 giant planets with massive gaseous envelopes, and a stable asteroid belt that provides a sample library of early solar system materials. The giant planets occupy nearly circular orbits that have remained stable for billions of years. Earth maintains a moderate climate suitable for liquid water, despite receiving constant bombardment by asteroids and comets. Our moon stabilizes Earth's rotational axis, preventing chaotic climate variations that would make complex life difficult. Understanding how our solar system formed is not merely an academic exercise. This knowledge helps us evaluate the likelihood of finding habitable worlds around other stars. It reveals the conditions necessary for stable planetary systems and the factors that might make Earth-like worlds rare or common in the universe. It also helps us assess potential threats to our own planet from asteroids, comets, and long-term changes in solar luminosity. The story you are about to hear spans more than 10 billion years, from the formation of the first stars to the present day. It involves temperatures ranging from absolute zero in the depths of interstellar space to hundreds of millions of degrees in stellar cores. It encompasses distances from the microscopic scale of dust grain collisions to the vast reaches of the Oort cloud at the edge of our solar system. Most importantly, it explains how the random motions of gas and dust in a molecular cloud ultimately produced the only known planet harboring life in the universe. Every chapter of this cosmic epic builds upon the previous one, creating an unbroken chain of cause and effect that connects the death of ancient stars to the origin of life on Earth. You will discover how the laws of physics, operating with mathematical precision across vast scales of space and time, transformed chaos into order and created the stable, habitable world we call home. The universe began in a state so extreme that matter as we know it could not exist. In the first microseconds after the Big Bang, temperatures exceeded 10 to the power of 12 Kelvin, hot enough to prevent even protons and neutrons from forming stable configurations. As the universe expanded and cooled, the fundamental forces we observe today separated from a unified field, and the first atomic nuclei began to assemble through a process called Big Bang nucleosynthesis. Within the first 20 minutes of cosmic history, nuclear reactions produced primarily hydrogen and helium, with trace amounts of lithium and beryllium. The ratio of these elements was determined by the expansion rate of the universe, the density of ordinary matter, and the fundamental constants governing nuclear physics. Approximately 75% of normal matter emerged as hydrogen, with 25% as helium. This primordial composition would dominate the universe's chemistry for hundreds of millions of years. The absence of elements heavier than lithium in the primordial universe created a fundamental problem for planet formation. Carbon, oxygen, silicon and iron, the building blocks of rocky worlds, did not exist. The first generation of stars, known as population 3 stars, formed from clouds of pure hydrogen and helium. These primordial giants were likely hundreds of times more massive than our Sun, burning through their nuclear fuel in just a few million years before exploding as supernovae. Population 3 supernovae performed the universe's first act of stellar nucleosynthesis, forging heavy elements through rapid neutron capture and explosive nuclear burning. Silicon-burning reactions produced iron, nickel, and cobalt. Alpha-process nucleosynthesis created elements like oxygen, neon, and magnesium. Rapid neutron capture during the supernova explosion generated elements heavier than iron through what astronomers call the R process. These stellar explosions dispersed newly formed heavy elements into the surrounding interstellar medium, enriching it with the raw materials needed for rocky planet formation. The transition from population 3 to population 2 stars marked a crucial phase in cosmic chemical evolution. Population 2 stars contained small but measurable quantities of heavy elements, allowing different types of nuclear burning and stellar evolution. More importantly, the presence of heavy elements enabled the formation of dust grains in stellar atmospheres and supernova ejecta. These microscopic particles of silicate, graphite and metal oxides would later serve as condensation nuclei for planet formation. As the universe continued to expand and cool, gravity began organizing matter into increasingly complex structures. Dark matter, which interacts only through gravitational forces, formed the scaffolding upon which ordinary matter could collect. Computer simulations of structure formation reveal how tiny density fluctuations in the early universe grew through gravitational instability into vast cosmic web of filaments, sheets, and voids. At the intersections of these filaments, the first galaxies began to form. Galaxy formation required the interplay of gravity, gas dynamics, and stellar feedback. As gas clouds collapsed under their own gravity, conservation of angular momentum caused them to flatten into rotating disks. The first stars forming within these protogalaxies produced ultraviolet radiation that ionized surrounding hydrogen, creating expanding bubbles of hot gas. Supernova explosions drove galactic winds that expelled gas from small galaxies while enriching the intergalactic medium with heavy elements. The Milky Way galaxy formed through the merger of smaller galactic building blocks over billions of years. Archaeological studies of stellar populations reveal multiple generations of star formation, each characterized by increasing metallicity as successive generations of massive stars lived and died. The galaxy's spiral structure emerged from density wave perturbations that compressed gas and triggered star formation as material orbited the galactic center. Spiral arms play a crucial role in stellar and planetary system formation. As gas clouds encounter the gravitational potential of spiral density waves, they experience compression that can trigger gravitational collapse. The spiral pattern also segregates stellar populations by age and metallicity, with the youngest, most metal-rich stars concentrated in the spiral arms, where active star formation continues today. The location of star formation within a galaxy significantly impacts the prospects for planetary system formation. Stars forming in the galactic center experience intense radiation fields and frequent supernova explosions that can strip away planetary atmospheres. Stars in the outer regions of galaxies have low metallicity, providing insufficient heavy elements for substantial rocky planet formation. The galactic habitable zone, sometimes called the galactic Goldilocks zone, represents the range of galactic radii where conditions favor the formation and long-term stability of habitable planets. Our Sun formed in what astronomers classify as the galactic thin disk, approximately 26,000 light-years from the galactic center. This location places it within the galactic habitable zone, where metallicity is sufficiently high for rocky planet formation, but radiation environments remain moderate enough to allow atmospheric retention. The Sun's nearly circular galactic orbit has kept it within this favorable zone throughout its 4.5 billion-year lifetime. The chemical composition of our solar system reflects this galactic chemical evolution. Spectroscopic analysis of the Sun's photosphere reveals abundance patterns that match theoretical predictions for third-generation stellar nucleosynthesis. Elements like carbon and oxygen show isotopic ratios consistent with production in intermediate mass stars during their asymptotic giant branch phase. The presence of rare elements like gold and platinum indicates contribution from R-process nucleosynthesis, likely in neutron star mergers or rare types of supernovae. Understanding galactic chemical evolution helps explain why planetary systems like ours appear to be relatively uncommon. Most stars in the galaxy have lower metallicity than the Sun, reducing their capacity to form substantial rocky planets. The timing of heavy element enrichment also matters. Stars that formed too early in galactic history lacked sufficient solid-forming materials, while those forming much later may experience disruptive environments from ongoing star formation activity. The discovery of thousands of exoplanets has confirmed these theoretical expectations. Statistical analyses reveal strong correlations between stellar metallicity and the occurrence rate of rocky planets. Stars with iron abundances similar to or higher than the Sun are much more likely to host terrestrial planets in their habitable zones. This metallicity requirement may represent one of the most significant filters limiting the abundance of potentially habitable worlds in our galaxy. As we trace the cosmic story from Big Bang nucleosynthesis through galactic chemical evolution, we see how the universe gradually assembled the ingredients necessary for complex planetary systems. The death of countless massive stars enriched interstellar space with the heavy elements essential for rocky world formation. Galactic dynamics organized this enriched material into regions where new generations of metal-rich stars could form. The specific location and timing of our Sun's birth placed it in an optimal environment for developing a planetary system capable of supporting complex chemistry and ultimately life. This galactic context sets the stage for understanding why our particular planetary system formed with its distinctive architecture and composition. The heavy element abundance inherited from previous stellar generations would determine which types of solid materials could condense in different regions of the forming solar system. The relatively peaceful galactic environment would allow billions of years of stable evolution necessary for life to emerge and flourish on Earth. Deep within the constellation Orion, astronomers today observe vast molecular clouds where new stars are actively forming. These stellar nurseries provide a window into processes that occurred 4.5 billion years ago when our own solar system began its existence. The story of our Sun's birth begins in such a cloud, a cold, dense region of space where hydrogen molecules drifted in near-perfect silence, occasionally joining with dust grains and trace heavy elements inherited from the deaths of previous stellar generations. The molecular cloud that would give birth to our solar system stretched across dozens of light years and contained enough material to form thousands of stars. Temperatures within the cloud hovered just 10 to 20 degrees above absolute zero, cold enough for most gases except hydrogen and helium to freeze onto dust grain surfaces. This frigid environment was essential for gravitational collapse because thermal motion of gas particles provides pressure that opposes gravitational contraction. Several mechanisms can trigger the collapse of a molecular cloud region. Shock waves from nearby supernova explosions compress gas and dust, creating density enhancements that become gravitationally unstable. The passage of spiral density waves as the cloud orbits the galactic center can also initiate compression. Stellar winds from massive stars or the radiation pressure from bright stellar clusters can compress adjacent cloud regions. In some cases, the collision of two molecular clouds creates the conditions necessary for gravitational collapse. The initial collapse proceeded according to the principles of gravitational instability theory. Small regions within the molecular cloud experienced random density fluctuations due to turbulent motions and magnetic field variations. When a region's gravitational binding energy exceeded its internal thermal and magnetic pressure, it began to contract under its own gravity. The mathematics of this process follow from the Jeans instability criterion, which determines the minimum mass and size required for gravitational collapse to overcome thermal pressure. As the collapsing region contracted, conservation of angular momentum became critically important. Even the slight rotation present in the original molecular cloud amplified dramatically as the material contracted, following the same principle that causes figure skaters to spin faster when they pull their arms inwards. The combination of gravitational collapse and angular momentum conservation transformed a roughly spherical cloud region into a flattened, rotating disk structure. The formation of a circumstellar disk represents one of the most important developments in planetary system formation. Within this disk, material could orbit the central condensation in stable trajectories rather than falling directly inward. The disk also established temperature and pressure gradients that would determine where different types of solid materials could condense from the cooling gas. These gradients ultimately controlled the composition and structure of planets, forming at different orbital distances. During the initial collapse phase, gravitational potential energy converted into thermal energy, heating the infalling material. However, the presence of dust grains and molecular hydrogen allowed efficient cooling through infrared radiation. This cooling was essential for continued collapse, as excessive heating would have halted the contraction process through thermal pressure support. Molecular hydrogen proved particularly important because its rotational and vibrational energy levels provided numerous pathways for radiating away thermal energy. The central region of the collapsing cloud experienced the most extreme conditions. As material accumulated in the core, gravitational compression raised temperatures and pressures toward the thresholds required for nuclear fusion. However, reaching those thresholds required overcoming the Coulomb barrier that prevents hydrogen nuclei from approaching close enough to fuse. The process of stellar ignition depends on quantum tunneling effects that allow nuclear reactions to occur at temperatures lower than classical physics would predict. Theoretical models of stellar formation suggest that our proto-sun spent approximately 100,000 years in the gravitational collapse phase before central temperatures reached the 10 million degree threshold necessary for sustained hydrogen fusion. During this pre-main sequence phase, the forming star derived its energy from gravitational contraction rather than nuclear reactions. This phase, known as the Hayashi track, involved rapid luminosity changes as the stellar interior adjusted to the onset of nuclear burning. The ignition of nuclear fusion in the Sun's core marked a fundamental transition in the physics governing our developing planetary system. The sudden onset of nuclear energy generation created intense radiation pressure that halted further gravitational collapse. Stellar winds powered by the newly active Sun began interacting with the surrounding disk, creating complex magnetohydrodynamic phenomena that would influence subsequent planet formation processes. The early Sun was significantly more active than the quiet star we observe today. Young stars typically exhibit high levels of magnetic activity, producing powerful stellar flares and intense stellar winds. X-ray observations of young stellar clusters reveal luminosities hundreds of times greater than mature stars of similar mass. This enhanced activity results from rapid stellar rotation and the presence of strong magnetic fields generated by dynamo processes in the convective stellar interior. High-energy radiation from the young Sun had profound effects on the surrounding disk material. Ultraviolet photons dissociated molecular hydrogen and ionized metals, creating a plasma environment in the inner disk regions. This ionization enabled magnetic coupling between the star and disk, allowing the transfer of angular momentum that caused material to spiral inward toward the star, while the stellar rotation gradually slowed through magnetic braking. The disk surrounding the young Sun was not a uniform, quiescent structure, but a dynamic, turbulent environment. Magnetorotational instability generated turbulent motions that mixed material vertically and transported angular momentum outward, enabling continued accretion onto the central star. These turbulent motions also influenced the distribution of solid particles within the disk, concentrating them in certain regions while dispersing them in others. Temperature gradients within the disk created distinct chemical environments at different orbital radii. Close to the Sun, where temperatures exceeded 1000 degrees Celsius, only the most refractory materials like aluminum oxides and calcium-aluminum inclusions could condense from the gas phase. At intermediate distances, silicate minerals and metallic iron became stable. Beyond the snowline, located approximately 2.5 times Earth's current orbital distance, water ice could condense and remain stable. These condensation zones established the fundamental architecture that would control terrestrial planet formation. The inner regions, dominated by refractory and silicate materials, would produce small, dense, rocky worlds with thin atmospheres. The outer regions, where ices significantly augmented the solid material budget, would allow the formation of massive planetary cores capable of gravitationally capturing hydrogen and helium to become gas giant planets. Observational studies of young stellar systems reveal that circumstellar disks typically dissipate within 2 to 10 million years of stellar formation. This dissipation timeline establishes a critical constraint on planet formation processes. Any planets that require substantial gas envelopes must form before the disk gas is depleted. This timing constraint explains why gas giant formation represents such a narrow window in planetary system evolution. The mechanisms responsible for disk dissipation include photoevaporation driven by stellar ultraviolet radiation, accretion of material onto the central star, and possibly the formation of planets massive enough to clear gaps in the disk structure. High-energy photons from the star heat the disk surface layers to temperatures where gas can escape the gravitational potential well. Meanwhile, magnetorotational instability continues transporting material inward to feed the growing star. As the disk evolved, solid particles began the long process of accumulating into larger bodies. Micrometer-sized dust grains, remnants of previous stellar generations, provided the seeds for planetary formation. These grains, composed primarily of silicates, metal oxides and carbonaceous materials, contained the heavy elements essential for rocky planet formation. Their abundance and composition reflected the galactic chemical evolution that had enriched the molecular cloud with successive generations of stellar nucleosynthesis products. The transition from a turbulent, gas-rich disk to a system of solid planetary bodies represents one of the most complex problems in astrophysics. This transformation required overcoming numerous obstacles, including the rapid orbital decay of solid particles due to gas drag, the bouncing and fragmentation that occurs when solid bodies collide at high velocities, and the tendency of growing planetary embryos to migrate through gravitational interactions with disk gas. Understanding these early evolutionary phases provides crucial context for interpreting the final architecture of our solar system. The initial conditions established during stellar formation, the disk mass, temperature structure, composition gradients, and dissipation timescale, determined which types of planets could form and where they could survive. The violence and beauty of stellar birth created the stage upon which the more familiar drama of planetary formation would unfold. The transformation of microscopic dust grains into kilometer-sized planetesimals represents one of the most challenging problems in planetary formation theory. This process must overcome what astronomers call the meter-size barrier, a range of particle sizes where physical processes conspire to prevent further growth through simple collisional accumulation. Understanding how nature solved this problem reveals the intricate physics that governs the birth of worlds. Dust grains in the primordial solar disk began as survivors from previous stellar generations. Tiny crystals of olivine, pyroxene and metallic iron expelled from stellar atmospheres, along with carbonaceous materials and ice mantles that condensed in the cold depths of interstellar space. These particles, typically measuring between 1/10 and 1 micrometer in diameter, were small enough to remain coupled to the gas motions in the turbulent disk, while still possessing enough surface area for efficient sticking during low-velocity collisions. The initial growth phase proceeded through what physicists call hit-and-stick collisions. When two dust grains moving at relative velocities of less than 1 meter per second collided, electrostatic forces and van der Waals interactions caused them to adhere permanently. This process works efficiently for particles smaller than approximately 1 millimeter because their low masses result in gentle collision velocities that do not exceed the binding energy of intermolecular forces. Laboratory experiments have revealed the remarkable efficiency of this process under appropriate conditions. When silicate dust grains collide in vacuum at velocities below the fragmentation threshold, they form fluffy, highly porous aggregates with internal structures resembling three-dimensional spider webs. These dust bunnies can achieve sizes of several centimeters while maintaining densities less than 1% that of solid rock. As these fluffy aggregates continued growing through collisional accumulation, their physical properties began changing in ways that created new challenges for further growth. Larger particles became more susceptible to disruption by turbulent gas motions within the disk. Their increased cross-sectional area also enhanced the effects of gas drag, causing them to lose angular momentum and spiral inward toward the Sun, on timescales much shorter than the disk lifetime. The meter-size barrier emerges from this combination of effects. Particles in the size range from centimeters to meters experience the strongest coupling to gas drag, while still being vulnerable to disruption by turbulence and high-velocity collisions. Theoretical calculations suggest that bodies in this size range should spiral into the Sun within a few thousand years, far too quickly for further growth through conventional accumulation processes. Several mechanisms have been proposed to overcome this barrier. Streaming instabilities in the disk gas can concentrate solid particles into dense clumps that become gravitationally bound before gas drag can cause orbital decay. The gravitational collapse of these particle concentrations can directly form kilometer-sized planetesimals without requiring growth through the problematic meter-size range. Alternative models invoke turbulent concentration mechanisms that create local overdensities of solid material. When turbulent eddies in the disk gas compress solid particles beyond a critical density threshold, gravitational forces can overcome turbulent dispersion and initiate direct gravitational collapse. This process bypasses the need for gradual accumulation through the meter-size regime. Recent numerical simulations have revealed another promising mechanism, the sandpile effect. When dust particles settle toward the disk mid-plane, they can accumulate in dense layers that become gravitationally unstable. These layers fragment into gravitationally bound clumps that contract to form solid planetesimals. The process resembles an avalanche, where a gradual accumulation of material suddenly reaches a critical threshold and collapses rapidly. Once kilometer-sized planetesimals formed through any of these mechanisms, further growth proceeded through gravitational interactions and physical collisions. Bodies large enough to have their own gravitational fields could attract smaller particles and planetesimals, accelerating their growth through a process called gravitational focusing. The effectiveness of this process depends on the escape velocity of the growing body compared to the typical velocities of impacting projectiles. The transition from planetesimal accretion to oligarchic growth represents another crucial phase in planetary formation. As the largest bodies in a given region grew faster than their neighbors through gravitational focusing, they began to dominate the local dynamics. These planetary embryos carved out gravitational feeding zones around their orbits, accreting most of the available solid material within their reach, while preventing smaller bodies from growing to comparable sizes. Computer simulations of oligarchic growth reveal a characteristic outcome. Each annular region of the disk develops one or a few dominant bodies with masses roughly 10 to 100 times larger than the remaining planetesimals. These embryos represent the seeds of the terrestrial planets, with typical masses equivalent to our Moon or Mars. Their formation timescales depend on the local surface density of solid material and the efficiency of gravitational focusing. In the inner solar system, where high temperatures limited solid condensation to refractory and silicate materials, oligarchic growth produced relatively small embryos with masses between 1 and 10% of Earth's mass. The limited availability of solid material in these regions meant that achieving larger masses required very efficient accretion or the collision and merger of multiple embryos. Beyond the snow line, where water ice could condense and remain stable, the situation was dramatically different. The addition of ice to the inventory of solid materials increased the surface density of condensable matter by a factor of approximately 4. This enhanced solid budget allowed planetary embryos to grow to much larger masses, potentially reaching 10 to 20 Earth masses within the disk lifetime. The formation of these massive solid cores beyond the snowline created the possibility for gas giant planet formation. When a planetary embryo reaches a critical mass of approximately 10 to 15 Earth masses, its gravitational field becomes strong enough to bind a significant atmosphere of hydrogen and helium from the surrounding disk gas. This atmospheric mass eventually exceeds the solid core mass, creating the gas-dominated composition characteristic of Jupiter and Saturn. The timing of giant planet formation proved crucial for the subsequent evolution of the entire planetary system. Once Jupiter reached sufficient mass to open a gap in the disk gas through its gravitational influence, it began experiencing orbital migration through gravitational torques from the surrounding material. This migration could have dramatically altered the architecture of the inner solar system if not for complex dynamical interactions involving multiple growing planets. Gas giant formation also affected the delivery of volatile materials to the inner planets. Gravitational perturbations from Jupiter and Saturn scattered water-rich planetesimals throughout the solar system, with some impacting the forming terrestrial planets. This process, known as late accretion or the late heavy bombardment, may have delivered most of Earth's water and other volatile compounds after the primary accretion phase was complete. The final assembly of terrestrial planets required the collision and merger of planetary embryos through giant impacts. Computer simulations suggest that the 4 inner planets formed through the accumulation of approximately 50 to 100 Moon-to-Mars-sized embryos over time periods of 10 to 100 million years. These giant impacts were energetic enough to melt and vaporize large fractions of the colliding bodies, leading to global magma oceans and extensive atmospheric loss. One particularly significant giant impact may have formed our Moon through the collision of a Mars-sized impactor with the proto-Earth. This collision ejected vast amounts of material into Earth orbit, which subsequently coalesced into our unusually large satellite. The angular momentum transferred during this impact may also explain Earth's rapid rotation and the tilted orientation of its rotational axis. The stochastic nature of giant impact processes means that terrestrial planet formation involves significant random elements. Small changes in the timing, location, or magnitude of giant impacts could have produced very different planetary architectures. Some computer simulations generate systems with super-Earths in close orbits, while others produce systems with no terrestrial planets at all. The specific configuration of our solar system may represent just one possible outcome from a much larger range of possibilities. Understanding planetary accretion processes helps explain many observed characteristics of our solar system. The compositional gradients of the terrestrial planets reflect the temperature-dependent condensation of different materials in the primordial disk. The existence of gas giant planets beyond the snowline results from the enhanced solid material budget available in those regions. The asteroid belt represents a region where planetary growth was halted by gravitational perturbations from nearby Jupiter. Modern observations of exoplanetary systems have revealed an astonishing diversity of planetary architectures, most of which differ significantly from our solar system. Hot Jupiters orbit closer to their stars than Mercury orbits our Sun. Super-Earths with masses between Earth and Neptune populate regions where our solar system contains only asteroids. These discoveries demonstrate that planetary formation can produce a wide variety of outcomes depending on the specific conditions present in each system. The detailed physics of planetary accretion continues to challenge astronomers and planetary scientists. New discoveries about dust grain properties, turbulence in protoplanetary disks, and the efficiency of various growth mechanisms regularly require updates to theoretical models. However, the basic framework described here, growth from dust to planetesimals to embryos to planets, provides a robust foundation for understanding how gravity and physics transform cosmic dust into the diverse worlds that populate planetary systems throughout the universe. At the gravitational and energetic center of our planetary system lies a sphere of plasma so massive that it contains 99.8% of all matter within the Sun's gravitational influence. This nuclear furnace has maintained nearly constant energy output for 4.5 billion years through a carefully regulated fusion process that converts hydrogen into helium while liberating the energy that powers virtually every process on Earth and throughout the solar system. The Sun's energy generation occurs in its core, a region extending from the center to approximately 1/4 of the solar radius. Here, temperatures reach 15 million degrees Celsius, and pressures exceed 200 billion times Earth's atmospheric pressure at sea level. Under these extreme conditions, hydrogen nuclei possess sufficient kinetic energy to overcome their mutual electrostatic repulsion through quantum tunneling effects, enabling nuclear fusion reactions that would be impossible under less extreme conditions. The primary fusion process in the Sun follows what nuclear physicists call the proton-proton chain reaction. This multi-step process begins when two hydrogen nuclei, or protons, collide with sufficient energy to fuse despite their positive electrical charges. One proton transforms into a neutron through beta plus decay, producing a deuteron, a positron, and a neutrino. The deuteron subsequently fuses with another proton to form helium-3, releasing a gamma-ray photon. Finally, two helium-3 nuclei fuse to produce helium-4, releasing two protons that can participate in future reaction cycles. Each complete proton-proton chain converts 4 hydrogen nuclei into one helium nucleus, with a net mass decrease of approximately 0.7%. This missing mass transforms into energy according to Einstein's mass-energy equivalence relation, where energy equals mass times the speed of light squared. The energy released from each reaction cycle amounts to approximately 26.7 million electron volts, which may seem modest but becomes enormous when multiplied by the countless reactions occurring every second throughout the solar core. The Sun converts approximately 600 million tons of hydrogen into helium every second, releasing energy equivalent to 100 billion hydrogen bombs detonating continuously. However, this energy does not reach the solar surface immediately. High-energy gamma-ray photons produced by fusion reactions must undergo countless absorption and re-emission events as they migrate outward through increasingly cool and dense solar material. In the radiative zone, extending from the core to approximately 70% of the solar radius, energy transport occurs primarily through radiation. Photons random walk through this region, being repeatedly absorbed by atoms and re-emitted in random directions. The mean free path of photons in the radiative zone measures only centimeters, meaning that each photon undergoes millions of absorption-emission cycles during its outward journey. This tortuous path means that photons require approximately 100,000 years to travel from the core to the base of the convection zone. The outer 30% of the solar interior comprises the convection zone, where energy transport shifts from radiative to convective processes. Temperature gradients in this region become steep enough that thermal instabilities drive convective motions similar to those in boiling water. Hot plasma rises from deeper layers while cooler material sinks, creating circulation cells that efficiently transport energy to the solar surface. These convective motions generate the Sun's magnetic field through dynamo processes involving the interaction of plasma flows with existing magnetic fields. Differential rotation, where the solar equator rotates faster than the poles, stretches magnetic field lines and amplifies magnetic fields through a process called the omega effect. Convective motions twist and tangle these field lines, creating complex magnetic structures that eventually emerge at the solar surface as sunspots, flares, and coronal mass ejections. The solar surface, or photosphere, represents the visible layer where the Sun becomes transparent to optical radiation. Temperatures in the photosphere average approximately 5,800 degrees Celsius, cool enough for atoms to exist in their ground states and emit the characteristic absorption lines that allow spectroscopic analysis of solar composition. The photosphere exhibits a granular structure caused by convective cells rising from below, creating a constantly changing pattern of bright granules surrounded by darker intergranular lanes. Above the photosphere lies the chromosphere, a thin atmospheric layer where temperatures initially decrease with altitude before rising again in the transition region leading to the corona. The chromosphere appears reddish during solar eclipses due to emission from hydrogen atoms in excited states. Spicules, jet-like features extending upward from the chromosphere, may play important roles in heating the overlying corona through magnetic reconnection processes. The solar corona represents the Sun's outermost atmospheric layer, extending millions of kilometers into space with temperatures exceeding 1 million degrees Celsius. This extreme heating occurs through mechanisms that remain incompletely understood, involving magnetic field interactions, plasma wave dissipation, and possibly nanoflare heating from countless small magnetic reconnection events. The corona's high temperature gives it sufficient thermal energy to escape solar gravity, creating the solar wind that flows continuously throughout the solar system. Solar wind consists of charged particles, primarily protons and electrons, streaming outward at velocities between 300 and 800 kilometers per second. This supersonic flow carries magnetic field lines from the Sun throughout the solar system, creating the interplanetary magnetic field that influences planetary magnetospheres and atmospheric evolution. The solar wind pressure creates a bubble around the solar system called the heliosphere, which excludes most galactic cosmic rays from the inner solar system. The Sun's magnetic activity follows an 11-year cycle characterized by the periodic reversal of the global solar magnetic field. During solar maximum, numerous sunspots appear on the solar surface, accompanied by increased flare and coronal mass ejection activity. Solar minimum periods exhibit few sunspots and reduced magnetic activity. This cycle results from the complex interplay between differential rotation and convective dynamo processes within the solar interior. Sunspots appear as dark regions on the photosphere where strong magnetic fields suppress convective heat transport from below, creating areas approximately 1,500 degrees cooler than the surrounding photosphere. The magnetic field strengths in sunspot umbrae can reach several thousand times Earth's magnetic field intensity. Sunspot groups often exhibit complex magnetic field configurations that store enormous amounts of magnetic energy. Solar flares occur when magnetic field lines in active regions become tangled and suddenly reconnect, releasing stored magnetic energy as kinetic energy of charged particles and electromagnetic radiation. The largest flares can release energy equivalent to billions of hydrogen bombs, accelerating particles to significant fractions of light speed and producing intense bursts of X-rays and ultraviolet radiation that can affect Earth's ionosphere and disrupt radio communications. Coronal mass ejections represent even more dramatic manifestations of solar magnetic activity. These events eject billions of tons of plasma and magnetic field into interplanetary space at velocities that can exceed 1,000 kilometers per second. When directed toward Earth, coronal mass ejections can compress our magnetosphere, trigger intense aurora displays, and potentially damage satellite electronics and power distribution systems. The Sun's energy output has increased gradually throughout its main sequence lifetime as helium accumulation in the core increases the central density and temperature required to maintain pressure equilibrium. Theoretical models suggest that solar luminosity was approximately 30% lower 4 billion years ago than it is today. This gradual increase, known as the faint young sun paradox, creates challenges for understanding early Earth's climate, as geological evidence indicates liquid water existed on Earth's surface despite receiving less solar energy than should have been sufficient to prevent global freezing. Solar variability occurs on multiple timescales beyond the 11-year magnetic cycle. Observational records reveal longer-term variations, including the Maunder minimum from 1660 to 1710, when sunspot activity nearly ceased and Earth experienced unusually cold temperatures during the Little Ice Age. These variations may result from changes in the solar dynamo process or interactions between different magnetic field generation mechanisms operating within the solar interior. The Sun's influence on planetary atmospheres extends far beyond simply providing heat and light. High-energy ultraviolet and X-ray radiation photoionizes atmospheric constituents, creating ionospheres and driving photochemical reactions that can produce or destroy trace gases. On planets lacking strong magnetic fields, solar wind particles can directly impact atmospheric constituents, leading to gradual atmospheric erosion over geological timescales. Solar radiation pressure affects small particles throughout the solar system through the Poynting-Robertson effect, causing dust grains to spiral slowly inward toward the Sun. This process helps clear the inner solar system of debris while contributing to zodiacal dust clouds visible during twilight. Solar radiation pressure also influences comet tail formation and the trajectories of spacecraft equipped with solar sails. The Sun's gravitational influence extends far beyond the visible planets to the Oort cloud, located roughly 50,000 times Earth's orbital distance. Solar tidal forces in this distant realm can perturb comet orbits, occasionally sending these icy bodies on trajectories that bring them into the inner solar system, where solar heating creates their characteristic bright coma and tails. Understanding solar physics provides crucial context for interpreting planetary formation and evolution processes. The early Sun's enhanced activity levels during the T Tauri phase help drive disk dispersal through photoevaporation, while influencing atmospheric retention on newly formed planets. The Sun's steady energy output throughout most of Earth's history enabled the stable climate conditions necessary for biological evolution. Future changes in solar luminosity will eventually render Earth uninhabitable, demonstrating the intimate connection between stellar and planetary evolution. Modern space-based observatories continuously monitor solar activity to predict space weather events that can affect human technology and astronaut safety. This practical importance of solar physics underscores how understanding our star remains essential, not only for comprehending planetary system formation, but also for managing our technological civilization's interaction with the space environment. Mercury presents the most extreme example of planetary formation processes operating under intense solar radiation and gravitational forces. This innermost world bears the scars of violent impact history while preserving crucial evidence about the composition and temperature gradients present in the innermost regions of the early solar nebula. Its unusual physical properties, particularly its oversized iron core, provide fundamental insights into how terrestrial planets assembled from the swirling disk of dust and gas that surrounded the young Sun. With a mean distance of just 57.9 million kilometers from the Sun, Mercury occupies a position where surface temperatures swing from 427 degrees Celsius on the day side to minus 173 degrees Celsius on the night side. These extreme temperatures result from Mercury's eccentric orbit, combined with its slow rotational period, which creates a solar day lasting 176 Earth days. The planet's 3-to-2 spin-orbit resonance means that some regions experience prolonged periods of intense solar heating, while others remain in perpetual shadow. Mercury's most striking characteristic is its exceptionally high density of 5.4 grams per cubic centimeter, nearly equal to Earth's, despite Mercury's much smaller size. This density implies that Mercury contains a proportionally larger iron core than any other planet in the solar system. While Earth's iron core comprises approximately 30% of the planet's mass, Mercury's core accounts for roughly 60% of its total mass. This composition presents a fundamental puzzle. How did such a large iron core form in a planet that accreted relatively close to the Sun? Three primary hypotheses have been proposed to explain Mercury's iron-rich composition. The first suggests that Mercury formed from material in the innermost regions of the solar nebula, where high temperatures preferentially vaporize silicate minerals while allowing refractory metals to condense. Computer models of nebular chemistry indicate that at Mercury's orbital distance, temperatures may have exceeded 1,400 degrees Celsius, hot enough to keep most silicate materials in vapor form while allowing iron and other metals to condense into solid grains. The second hypothesis proposes that Mercury originally formed with a more typical silicate-to-iron ratio, but subsequently lost most of its silicate mantle through a giant impact early in solar system history. Such an impact would need to have been energetic enough to vaporize and strip away the outer rocky layers while leaving the dense iron core intact. The impacting body would need to have been approximately half Mercury's mass and traveling at velocities exceeding 20 kilometers per second to achieve the required energy density. A third possibility involves selective vaporization of silicate materials by intense solar radiation during Mercury's formation. Young stars typically exhibit luminosities and stellar wind intensities much higher than their mature counterparts. If the early Sun was significantly more active than today, intense radiation and particle bombardment might have preferentially removed lighter silicate materials from the inner solar system while leaving behind the more refractory iron-rich components. Recent analysis of data from NASA's Messenger spacecraft has provided new constraints on these competing hypotheses. Measurements of Mercury's surface composition reveal higher concentrations of sulfur, potassium and chlorine than predicted by simple condensation models. These volatile elements should have been depleted in the high-temperature environment near the Sun, yet their presence suggests that Mercury's formation was more complex than simple thermal equilibrium condensation. The discovery of these unexpected volatile elements supports scenarios involving either late-stage accretion of volatile-rich material or impact processes that mixed materials from different regions of the solar nebula. Some models propose that Mercury accreted a significant fraction of its mass from material that originally formed at greater distances from the Sun, but was subsequently scattered inward by gravitational interactions with the forming gas giant planets. Mercury's surface geology provides additional clues about its formation and early evolution. The planet's heavily cratered terrain preserves a record of the intense bombardment that characterized the early solar system. The largest impact structure, the Hellish Basin, spans approximately 1,500 kilometers in diameter and represents one of the most significant impact events in the inner solar system's recorded history. The formation of the Hellish Basin demonstrates the scale of collisional processes that shaped terrestrial planet formation. The impacting object must have been at least 100 kilometers in diameter and traveling at typical solar system encounter velocities of 20 to 40 kilometers per second. Such impacts release energy equivalent to millions of megatons of TNT, sufficient to melt and reshape vast regions of planetary crusts, while creating shockwaves that propagate through entire planetary bodies. Analysis of crater-sized frequency distributions on Mercury's surface reveals evidence for at least two distinct populations of impacting objects. The largest craters likely formed during the late heavy bombardment period, approximately 4 billion years ago, when dynamical instabilities in the outer solar system scattered populations of large asteroids and comets throughout the inner solar system. Smaller craters represent a more continuous population of debris that has impacted Mercury throughout solar system history. Mercury's lack of a substantial atmosphere results from its small mass and proximity to the Sun. The planet's escape velocity of just 4.3 kilometers per second is insufficient to retain most atmospheric gases at the high temperatures encountered near perihelion. Any atmosphere that might have existed during Mercury's formation would have been rapidly lost to space through thermal escape processes enhanced by intense solar radiation and particle bombardment. Despite the absence of a substantial atmosphere, messenger observations revealed the surprising presence of water ice deposits in permanently shadowed craters near Mercury's poles. These deposits exist because Mercury's small axial tilt means that polar regions remain perpetually shaded from direct sunlight, creating cold traps where temperatures remain below -150 degrees Celsius, even at Mercury's closest approach to the Sun. The presence of water ice on Mercury provides important constraints on volatile delivery mechanisms throughout the solar system. The ice likely originated from comet impacts that occurred after Mercury's formation was essentially complete. Computer simulations suggest that a small fraction of water delivered by comet impacts can become trapped in polar cold traps, even on planets as close to the Sun as Mercury, provided that sufficient quantities are delivered over geological timescales. Mercury's magnetic field, though weak compared to Earth's, indicates the presence of an active dynamo process within its iron core. Magnetic field measurements suggest that approximately 75% of Mercury's radius consists of liquid iron, making it the most iron-rich planet in the solar system by volume as well as mass. The dynamo mechanism responsible for generating Mercury's magnetic field likely involves convective motions driven by cooling and crystallization of the liquid iron core. The slow rotation of Mercury presents challenges for dynamo theory, as most models require relatively rapid rotation to generate the fluid motions necessary for magnetic field generation. Recent theoretical work suggests that Mercury's dynamo might be driven by compositional convection associated with light element separation during core crystallization, rather than thermal convection alone. This mechanism could operate effectively even at Mercury's slow rotation rate. Mercury's orbital characteristics preserve information about dynamical processes during terrestrial planet formation. The planet's high orbital eccentricity of 0.206 is the largest among the solar system's planets, suggesting that Mercury experienced significant gravitational perturbations during its formation. Computer simulations of terrestrial planet assembly often produce Mercury analogues with similarly eccentric orbits through gravitational interactions during the final stages of planetary accretion. The study of Mercury provides crucial tests for theoretical models of terrestrial planet formation. Its extreme composition and orbital characteristics represent boundary conditions that successful formation theories must be able to reproduce. Understanding how Mercury acquired its iron-rich composition while retaining unexpected volatile elements continues to challenge our understanding of physical and chemical processes operating in the innermost regions of planetary systems. Comparative studies of Mercury, with exoplanets orbiting close to their parent stars, reveal both similarities and differences that illuminate planetary formation processes. Many exoplanetary systems contain super-Earths and mini-Neptunes in orbital positions closer to their stars than Mercury is to our Sun. These planets appear to have retained substantial atmospheres despite their proximity to intense stellar radiation, suggesting that planetary mass plays a crucial role in atmospheric retention. The extreme environment near Mercury also provides insights into space weathering processes that affect airless bodies throughout the solar system. Solar wind bombardment and micrometeorite impacts gradually alter surface mineralogy and optical properties through processes that operate on all atmosphere-free worlds. Understanding these processes on Mercury helps interpret observations of asteroids, moons, and other small bodies that lack protective atmospheres. As we continue studying Mercury through ongoing spacecraft missions and theoretical modeling, this innermost planet serves as a natural laboratory for understanding how planets form and evolve under the most extreme conditions found in our solar system. Its unique characteristics provide essential constraints on the physical and chemical processes that operated during the solar system's violent youth, when colliding planetesimals and intense radiation shaped the worlds that would become our cosmic neighbors. Venus presents one of the most dramatic examples of how small changes in planetary formation conditions can lead to radically different evolutionary outcomes. Often called Earth's twin due to similar size and bulk composition, Venus has evolved into a hellish world where surface temperatures exceed 460 degrees Celsius and atmospheric pressures reach 90 times Earth's sea level values. This extreme climate results from a runaway greenhouse effect that transformed what might once have been an Earth-like world into the solar system's most inhospitable planetary surface. The formation of Venus occurred in a region of the solar nebula where temperatures were only slightly higher than those experienced during Earth's accretion. At Venus's orbital distance of 108 million kilometers from the Sun, Silicate minerals and metallic iron could condense efficiently, providing abundant solid material for terrestrial planet formation. However, this proximity to the Sun, receiving approximately twice Earth's solar radiation, would prove crucial in determining Venus's subsequent atmospheric evolution. During the early phases of terrestrial planet formation, Venus likely accreted through processes similar to those that formed Earth and Mars. Planetary embryos with masses comparable to our Moon or Mars collided and merged through giant impacts that delivered both solid material and volatile compounds. Water arrived through asteroid and comet impacts, while other atmospheric constituents outgassed from the planet's interior during the intense heating associated with accretionary collisions. The key difference in Venus's evolution emerged during the critical first billion years, when atmospheric composition and surface temperature established a delicate balance between liquid water, stability, and runaway evaporation. Computer models of early atmospheric evolution suggest that Venus may have initially possessed liquid water oceans similar to those that existed on early Earth. However, the higher solar flux received at Venus's orbital distance created conditions where this balance proved unstable. The runaway greenhouse effect begins when atmospheric water vapor concentrations increase beyond a critical threshold. Water vapor is an extremely effective greenhouse gas that absorbs infrared radiation emitted by planetary surfaces. As surface temperatures rise due to enhanced greenhouse heating, more water evaporates from oceans and other surface reservoirs. This additional water vapor enhances the greenhouse effect further, creating a positive feedback loop that continues until all available water has evaporated into the atmosphere. Once water vapor reaches the upper atmosphere, ultraviolet radiation from the Sun dissociates water molecules into hydrogen and oxygen atoms. Hydrogen, being the lightest element, escapes to space relatively easily, while oxygen typically combines with surface materials through oxidation reactions. This process, called hydrodynamic escape, can completely remove a planet's water inventory over geological timescales, leaving behind a dry carbon dioxide-dominated atmosphere. Venus's current atmosphere consists of approximately 96% carbon dioxide, with trace amounts of nitrogen, sulfur dioxide and other compounds. The absence of water vapor and the dominance of carbon dioxide create an extremely efficient greenhouse effect that maintains surface temperatures hot enough to melt lead. This composition likely represents the endpoint of atmospheric evolution following the loss of hydrogen through hydrodynamic escape. The thick atmosphere creates a surface pressure equivalent to being 1 kilometer underwater on Earth. This extreme pressure results from the large mass of gas in Venus's atmosphere, approximately 90 times more massive per unit surface area than Earth's atmosphere. The high density and pressure create unique atmospheric dynamics, including extremely slow winds at the surface but high velocity circulation in the upper atmosphere. Venus's atmospheric circulation exhibits a phenomenon called superrotation, where upper atmosphere winds circle the planet in just 4 Earth days, while the solid planet below rotates once every 243 Earth days in the opposite direction. This retrograde rotation remains one of the most puzzling aspects of Venus's current state. Possible explanations include tidal interactions with the Sun, atmospheric tides, or the effects of a giant impact that altered the planet's original spin state. The dense atmosphere creates a powerful greenhouse effect, but also transports heat very efficiently from day to night sides, minimizing temperature variations across the planet's surface. Despite receiving no direct sunlight, Venus's night side maintains nearly the same temperature as regions experiencing full solar illumination. This efficient heat transport results from the high atmospheric density and active convective circulation throughout the lower atmosphere. Venus's surface features provide important clues about its geological evolution and internal dynamics. Radar mapping by the Magellan spacecraft revealed a surface dominated by volcanic features including vast lava plains, shield volcanoes and complex coronae structures that may result from mantle plume activity. Approximately 80% of Venus's surface consists of volcanic plains that appear relatively young based on their low crater densities. The apparent youth of Venus's surface suggests that global resurfacing events may have occurred within the past billion years. Some researchers propose that Venus experiences episodic overturn events where the entire surface is renewed through massive volcanic outpouring driven by mantle overturn processes. Alternative models suggest more gradual resurfacing through localized volcanic activity similar to terrestrial plate tectonics. The absence of obvious plate tectonic features on Venus contrasts sharply with Earth's active surface geology. Venus lacks the network of mid-ocean ridges, transform faults and subduction zones that characterize terrestrial plate tectonics. This difference may result from Venus's dry interior conditions, as water plays crucial roles in lubricating plate motions and generating the partial melting that creates new oceanic crust on Earth. Without water to facilitate plate tectonics, Venus's interior heat must escape primarily through conductive cooling and localized volcanic activity. This may lead to different patterns of mantle convection and surface volcanism compared to water-bearing planets. Computer simulations suggest that Venus's mantle may experience periodic overturn events where hot material from deep in the interior rises rapidly to the surface, creating episodes of intense global volcanism. Venus's lack of a significant magnetic field indicates the absence of an active dynamo process in its core. This differs from Earth, Mars and Mercury, all of which show evidence for current or past magnetic field generation. The absence of a Venusian magnetic field may result from slow planetary rotation, a solid rather than liquid iron core, or different thermal evolution pathways that prevented the establishment of convective motions necessary for dynamo action. Without a magnetic field to deflect solar wind particles, Venus's upper atmosphere interacts directly with the solar wind through processes that may contribute to continued atmospheric loss. High-energy particles can knock atmospheric constituents into space through sputtering processes, while magnetic reconnection events can create channels for atmospheric escape. However, Venus's massive atmosphere means that these loss processes operate on timescales much longer than the age of the solar system. The study of Venus's atmospheric composition provides insights into volatile inventories and outgassing processes during terrestrial planet formation. Noble gas ratios in Venus's atmosphere differ from those found in Earth's atmosphere, suggesting different origins or evolutionary pathways for these trace constituents. The high concentration of primordial argon indicates extensive outgassing from Venus's interior, while isotopic ratios of other elements provide constraints on atmospheric escape processes. Carbon dioxide isotope ratios on Venus show evidence for fractionation processes that occur during atmospheric escape. Lighter isotopes escape preferentially, leaving the remaining atmosphere enriched in heavier isotopes. The magnitude of this fractionation provides estimates for the total amount of atmospheric loss that has occurred throughout Venus's history, though uncertainties remain about the initial isotopic composition and the efficiency of different escape mechanisms. Recent detections of phosphine in Venus's upper atmosphere have generated significant scientific interest due to phosphine's potential biological origin on Earth. However, the extreme surface conditions on Venus make biological explanations unlikely, and researchers are investigating various abiotic processes that might produce phosphine in Venus's unique atmospheric chemistry. These discoveries highlight how much remains unknown about atmospheric chemical processes on Venus. Understanding Venus's evolution provides crucial insights into planetary habitability and the factors that determine whether Earth-like worlds can maintain stable, temperate climates over geological timescales. The runaway greenhouse effect that transformed Venus demonstrates how proximity to a star can create unstable climate conditions even for planets that initially possess abundant liquid water. Comparative planetology studies use Venus as an example of how planetary climate systems can evolve along very different pathways despite similar initial conditions. The contrast between Venus's extreme greenhouse climate and Earth's temperate conditions illustrates the importance of feedback mechanisms in determining long-term climate stability. These lessons prove crucial for understanding the potential habitability of exoplanets orbiting in the inner regions of other stellar systems. As we continue studying Venus through future missions and theoretical modeling, this infernal world serves as a natural laboratory for understanding atmospheric physics under extreme conditions. Its evolutionary history provides essential insights into the physical and chemical processes that determine whether terrestrial planets can maintain the stable, moderate climates necessary for sustaining liquid water and potentially life on their surfaces. Earth represents the most complex outcome of terrestrial planet formation processes, having evolved from a molten, chaotic assemblage of colliding planetesimals into the only known world harboring life. This extraordinary transformation required precise coordination of physical, chemical and dynamical processes operating over nearly 5 billion years. Understanding Earth's formation and evolution reveals the delicate balance of conditions necessary to create and maintain a habitable world in an otherwise hostile universe. The formation of Earth began approximately 4.54 billion years ago through the accretion of solid materials in the habitable zone of the solar nebula. This region, located between approximately 0.9 and 1.7 astronomical units from the Sun, provided conditions where liquid water could exist on planetary surfaces given appropriate atmospheric compositions. However, the early Earth bore little resemblance to the temperate world we know today. During the first several hundred million years of Earth's existence, the planet experienced continuous bombardment by asteroids, comets and planetary embryos in a violent process that kept the surface largely or completely molten. The energy released by these constant impacts, combined with heat generated by gravitational compression and radioactive decay, maintained a global magma ocean hundreds of kilometers deep. This molten state enabled efficient chemical differentiation as dense materials sank toward the center, while lighter components rose to form primitive crustal materials. The most significant event in early Earth history occurred when a Mars-sized planetary embryo called Theia collided with the proto-Earth approximately 4.5 billion years ago. This giant impact vaporized much of both bodies, ejecting enormous quantities of material into Earth orbit. The impact energy was sufficient to completely melt Earth's mantle and may have vaporized any existing oceans or atmosphere. Most of the ejected material subsequently coalesced to form the Moon, while the remainder eventually reaccreted onto Earth. The moon-forming impact had profound consequences for Earth's subsequent evolution. The collision transferred substantial angular momentum to the Earth-Moon system, giving Earth its current 24-hour rotation period and establishing the Moon's orbital motion. The presence of a large satellite stabilized Earth's rotational axis, preventing the chaotic climate variations that would result from large changes in axial tilt. The Moon also generates tidal forces that may have played important roles in the origin and evolution of life. Following the Moon-forming impact, Earth required several 100 million years to cool sufficiently for liquid water to condense and remain stable on its surface. During this period, volcanic outgassing from the interior contributed water vapor, carbon dioxide, nitrogen, and other gases that formed Earth's secondary atmosphere. The composition of this early atmosphere differed dramatically from today's oxygen-rich environment, containing primarily carbon dioxide, nitrogen, and water vapor, with trace amounts of methane, ammonia, and hydrogen sulfide. The establishment of stable oceans marked a crucial transition in Earth's evolution from a largely sterile world to one capable of supporting life. Liquid water provided the medium necessary for complex chemical reactions that could assemble organic molecules and eventually living systems. The presence of oceans also began moderating Earth's climate through the hydrological cycle, which transports heat from equatorial regions to higher latitudes while removing carbon dioxide from the atmosphere through carbonate mineral formation. Earth's early atmosphere contained virtually no free oxygen, which would have been toxic to the first living organisms. The absence of oxygen meant that Earth's surface received much higher levels of ultraviolet radiation from the sun, as there was no ozone layer to filter these harmful wavelengths. Early life forms must have been adapted to these harsh radiation conditions, possibly living in protected environments such as deep ocean thermal vents or beneath protective layers of rock or water. The origin of life on Earth remains one of the most challenging scientific questions, but several lines of evidence suggest it occurred relatively early in Earth's history. The oldest potential fossils date to approximately 3.5 billion years ago, while isotopic evidence for biological processes may extend back 3.8 billion years. This means life emerged within the first billion years of Earth's existence, despite the hostile conditions that prevailed during this period. Early life forms were exclusively prokaryotic organisms lacking membrane-bound organelles or complex cellular structures. These primitive bacteria and archaea obtained energy through various chemosynthetic processes that did not require oxygen or sunlight. Some early organisms may have lived near hydrothermal vents on the ocean floor, deriving energy from chemical reactions involving hydrogen sulfide, iron, or other reduced compounds abundant in these environments. The evolution of photosynthesis represents one of the most significant developments in Earth's history, ultimately transforming both the atmosphere and the possibilities for life. The first photosynthetic organisms likely used hydrogen sulfide or other reduced compounds as electron donors, but eventually evolved the ability to extract electrons from water molecules. This oxygenic photosynthesis began releasing free oxygen into the atmosphere as a waste product, setting the stage for a dramatic environmental transformation. The accumulation of oxygen in Earth's atmosphere occurred gradually over approximately 2 billion years in what geologists call the Great Oxidation Event. Initially, most oxygen produced by photosynthesis was consumed by reactions with reduced iron and sulfur compounds in the oceans and atmosphere. However, once these oxygen sinks became saturated, free oxygen began accumulating in the atmosphere, rising from essentially 0 to several percent of current levels by 2 billion years ago. The rise of atmospheric oxygen had profound consequences for life and Earth's surface chemistry. Many existing organisms found oxygen toxic and either adapted to the new conditions, retreated to oxygen-free environments, or went extinct. However, organisms that evolved the ability to use oxygen for cellular respiration gained access to much more efficient energy production pathways. Aerobic respiration yields approximately 18 times more energy per glucose molecule than anaerobic alternatives, enabling the evolution of larger, more complex organisms. Atmospheric oxygen also enabled the formation of the ozone layer, which absorbs harmful ultraviolet radiation and creates a protective shield around Earth. This development allowed life to colonize shallow marine environments and eventually terrestrial habitats that had previously been uninhabitable due to high radiation levels. The ozone layer essentially opened up new ecological niches that could support increasingly complex ecosystems. The evolution of eukaryotic cells approximately 2 billion years ago represents another major milestone in Earth's biological evolution. Eukaryotes possess membrane-bound organelles, including nuclei, mitochondria, and chloroplasts that enable much more sophisticated cellular organization and metabolism. The development of sexual reproduction among eukaryotes accelerated evolutionary processes by increasing genetic diversity and enabling more rapid adaptation to changing environmental conditions. Multicellular organisms first appeared in the fossil record approximately 1 billion years ago, though they remained microscopic and relatively simple for several 100 million years. The evolution of complex multicellular life required the development of mechanisms for cellular differentiation, intercellular communication, and coordinated growth and development. These innovations eventually led to the emergence of macroscopic organisms during the Ediacaran period, approximately 600 million years ago. The Cambrian explosion, beginning approximately 540 million years ago, marked the relatively rapid appearance of most major animal phyla in the fossil record. This biological innovation coincided with rising oxygen levels that crossed critical thresholds for supporting active, mobile organisms with high metabolic demands. The development of hard shells, exoskeletons, and other mineralized structures during this period greatly improved fossilization potential, creating the rich fossil record that documents subsequent evolutionary history. Throughout Earth's history, the evolution of life has been intimately connected with changes in atmospheric composition, ocean chemistry, and climate. Major extinction events often correspond with episodes of volcanism, asteroid impacts, or other environmental perturbations that disrupted established ecosystems. However, life has consistently recovered from these setbacks and often evolved new forms better adapted to changed environmental conditions. The most recent major development in Earth's biological evolution has been the emergence of intelligence and technological civilization. Humans represent the first species capable of significantly modifying global environmental conditions through technology. This capability brings both opportunities and responsibilities for managing Earth's future evolution and maintaining the conditions necessary for continued habitability. Earth's magnetic field, generated by convective motions in the liquid iron outer core, provides crucial protection from solar wind particles and cosmic radiation. The magnetic field deflects charged particles that would otherwise interact directly with the atmosphere, potentially leading to atmospheric loss over geological timescales. Variations in magnetic field intensity and occasional magnetic reversals may have influenced biological evolution by modulating radiation exposure levels. Plate tectonics represents another unique aspect of Earth among terrestrial planets, driven by mantle convection and facilitated by the presence of liquid water. The continuous recycling of crustal materials through subduction zones helps regulate atmospheric carbon dioxide levels by burying organic carbon and carbonate minerals in the deep Earth. Volcanic activity at mid-ocean ridges and continental margins returns volatiles to the surface, maintaining the atmospheric inventory necessary for climate stability. The carbon cycle represents one of Earth's most important regulatory systems, maintaining atmospheric carbon dioxide concentrations within ranges compatible with liquid water stability. Weathering of silicate rocks consumes atmospheric carbon dioxide, while volcanism returns carbon dioxide to the atmosphere. This system provides negative feedback that helps stabilize Earth's climate over geological timescales, preventing both runaway greenhouse warming and complete glaciation. Earth's current position in the solar system places it within the continuously habitable zone, where liquid water can exist throughout stellar evolution. As the Sun gradually increases in luminosity over billions of years, this habitable zone moves outward, but Earth's orbit should remain within habitable limits for approximately another billion years. However, various positive feedback processes may render Earth uninhabitable sooner than simple stellar evolution models predict. Understanding Earth's formation and evolution provides the foundation for assessing the likelihood of finding similar habitable worlds around other stars. The specific combination of factors that enabled Earth's evolution, appropriate stellar type and luminosity, orbital distance, planetary mass, presence of liquid water, magnetic field, plate tectonics, and atmospheric composition, may be relatively rare among planetary systems throughout the galaxy. As we continue studying Earth's history through geological, biological, and atmospheric research, our home planet serves as the primary reference point for understanding habitability requirements and the factors that enable worlds to support complex life. These insights prove essential for interpreting observations of exoplanets and assessing their potential for harboring life beyond our solar system. Mars stands as perhaps the most poignant example of how planetary formation and evolution can lead to dramatically different outcomes despite similar starting conditions. Often called Earth's smaller sibling, Mars formed in a region of the solar nebula where conditions initially seemed favorable for developing another habitable world. However, fundamental differences in mass, orbital distance, and subsequent evolutionary pathways transformed Mars from a potentially warm, wet world into the cold, dry desert planet we observe today. The formation of Mars occurred at approximately 1.5 astronomical units from the Sun, well within the region where liquid water could exist on planetary surfaces given appropriate atmospheric conditions. During the early phases of terrestrial planet accretion, Mars accumulated solid materials through the same processes of planetesimal collision and gravitational focusing that formed Earth and Venus. However, Mars's location near the inner edge of the asteroid belt meant that its growth was significantly affected by gravitational perturbations from the forming giant planets. Computer simulations of terrestrial planet formation reveal that Mars represents a planetary embryo that never achieved its full growth potential. Jupiter's formation and subsequent orbital evolution created dynamical instabilities that scattered planetesimals throughout the inner solar system while preventing efficient accretion in the Mars region. This process, sometimes called the Grand Tack model, explains both Mars's small size and the current structure of the asteroid belt as a population of leftover planetary building blocks. With a mass only 11% of Earth's and a diameter approximately half of Earth's, Mars lacks the gravitational field strength necessary to retain substantial atmospheres over geological timescales. The planet's escape velocity of 5 kilometers per second is significantly lower than Earth's 11.2 kilometers per second, making it much easier for atmospheric gases to achieve sufficient thermal velocities to escape to space, particularly when heated by solar ultraviolet radiation or energetic particle bombardment. Despite its small size, early Mars appears to have possessed a substantial atmosphere and possibly global or regional seas during the first billion years of solar system history. Evidence for this wetter, warmer past comes from multiple sources, including ancient riverbeds, lake deposits, hydrated minerals, and isotopic signatures in the current thin atmosphere that indicate substantial atmospheric loss over geological time. The Martian surface preserves an extraordinary record of ancient environmental conditions through geological features that formed under very different climate conditions than exist today. Extensive networks of dendritic valleys resembling terrestrial river systems indicate that liquid water flowed across the Martian surface for extended periods during the planet's early history. These valley networks are most abundant in the ancient, heavily cratered terrains that formed more than 3.5 billion years ago. Some of the most impressive evidence for ancient water activity on Mars comes from sedimentary deposits left by lakes and rivers. The Mars Science Laboratory rover Curiosity has analysed mudstone formations in Gale Crater that formed in a lake environment with neutral pH and chemical conditions that could have supported microbial life. These deposits contain organic molecules and evidence for past environmental conditions that included flowing water, moderate temperatures, and chemical energy sources that life could potentially exploit. The transition from early Mars's potentially habitable conditions to its current frozen desert state represents one of the most dramatic climate changes documented in the solar system. This transformation likely resulted from the combined effects of atmospheric loss, declining volcanic activity, and possibly changes in orbital parameters or obliquity that affected seasonal and latitudinal distribution of solar heating. Atmospheric loss on Mars occurs through several mechanisms that operate much more efficiently than on Earth due to Mars's weak gravitational field and lack of a strong magnetic field. Thermal escape allows light gases like hydrogen to achieve velocities exceeding escape velocity when heated in the upper atmosphere. Non-thermal escape processes, including sputtering by solar wind particles and pick-up ion acceleration, can remove heavier atmospheric constituents that would not escape through thermal processes alone. The absence of a strong Martian magnetic field plays a crucial role in atmospheric loss processes. Unlike Earth, where the magnetic field deflects solar wind particles and prevents their direct interaction with atmospheric constituents, Mars's weak magnetic field provides minimal protection. Solar wind particles can penetrate deep into the Martian atmosphere, transferring energy to atmospheric gases and facilitating various escape mechanisms. Mars does possess localized magnetic field regions, particularly in the southern highlands, that provide evidence for an ancient global magnetic field that operated during the first few 100 million years of Martian history. The cessation of this magnetic field likely resulted from cooling of the Martian core below the temperature necessary to maintain convective motions and dynamo action. The timing of magnetic field loss may have accelerated atmospheric loss and contributed to the transition from early habitable conditions to the current harsh environment. Isotopic analysis of the current Martian atmosphere provides quantitative constraints on the amount of atmospheric loss that has occurred throughout Martian history. The ratio of deuterium to hydrogen in Martian water vapor is approximately 6 times higher than in Earth's oceans, indicating preferential loss of lighter hydrogen isotopes over geological time. This fractionation suggests that Mars has lost the equivalent of a global water layer several hundred meters deep, though the original water inventory may have been distributed as atmospheric water vapor rather than surface oceans. Similarly, isotopic ratios of carbon and noble gases in the Martian atmosphere show evidence for extensive atmospheric loss. The current atmospheric pressure of approximately 6 millibars represents only a tiny fraction of the atmosphere that likely existed during Mars's early history. Estimates based on isotopic fractionation and geological evidence suggest that early Mars may have possessed atmospheric pressures several hundred times higher than current values. The geological history of Mars is divided into 3 major periods based on crater density and geological activity. The Noachian period, spanning from approximately 4.1 to 3.7 billion years ago, represents the era when most evidence for abundant liquid water activity was preserved. This period corresponds with the heavy bombardment epoch when impact rates were high throughout the inner solar system. The Hesperian period, from approximately 3.7 to 3 billion years ago, shows evidence for continued but declining water activity, along with extensive volcanic resurfacing in regions like Tharsis and Elysium. The most recent Amazonian period, covering the past 3 billion years, is characterized by minimal water activity, reduced volcanism, and the gradual evolution toward current desert conditions. Mars's volcanic history provides important insights into the planet's internal evolution and its capacity to release atmospheric gases through outgassing. The Tharsis volcanic province contains some of the largest volcanoes in the solar system, including Olympus Mons, which rises approximately 27 kilometers above the surrounding terrain. These massive shield volcanoes formed through hotspot volcanism, similar to Hawaiian volcanoes, but achieved much larger sizes due to Mars's lower gravity and lack of plate tectonics that would have moved the surface away from underlying mantle plumes. The formation and evolution of Tharsis had profound effects on Martian geology and potentially climate. The enormous mass of volcanic material in this region created gravitational anomalies that influenced global circulation patterns and may have affected the stability of any early oceans. Some models suggest that Tharsis volcanism could have released sufficient water vapor and carbon dioxide to maintain warm, wet conditions during portions of Martian history. The dichotomy between Mars's northern and southern hemispheres represents one of the most striking features of Martian geology. The southern hemisphere consists of heavily cratered highlands elevated several kilometers above the northern plains, while the northern hemisphere shows evidence for extensive resurfacing and possibly ancient ocean basins. This fundamental asymmetry may have resulted from a giant impact during early Martian history that created the northern lowlands. Evidence for ancient oceans in Mars's northern hemisphere includes shoreline features at consistent elevations, sedimentary deposits characteristic of marine environments, and geochemical signatures in meteorites that suggest interaction between rocks and large bodies of standing water. However, the existence and extent of Martian oceans remains controversial, with alternative explanations involving localized lakes or groundwater systems rather than true ocean basins. The search for past or present life on Mars has become one of the primary objectives of planetary exploration. The discovery of potentially habitable environments during Mars's early history, combined with the preservation of organic molecules in ancient sediments, suggests that Mars may have supported microbial life during its warmer, wetter past. Current missions are analyzing samples from various geological environments to search for biosignatures that would indicate past biological activity. Seasonal changes on present-day Mars provide insights into current atmospheric and surface processes. The planet's elliptical orbit and 25-degree axial tilt create seasonal variations in temperature and atmospheric pressure. During southern summer, when Mars is closest to the Sun, dust storms can engulf the entire planet, while polar ice caps of carbon dioxide and water ice advance and retreat with the seasons. The Martian moons, Phobos and Deimos, are small, irregular bodies that likely represent captured asteroids rather than objects that formed with Mars through accretion processes. Their compositions appear similar to carbonaceous asteroids, and their orbits suggest capture from the nearby asteroid belt. However, the mechanism and timing of their capture remains uncertain, with some models suggesting they formed from debris generated by giant impacts on Mars. Subsurface water ice on Mars represents a potentially important resource for future exploration, and possibly a refugium for any surviving Martian life. Ground-penetrating radar and neutron spectroscopy have revealed extensive ice deposits at high latitudes and possibly at lower latitudes beneath protective layers of dust and rock. These ice deposits may preserve records of past climate conditions and could potentially harbour dormant or active microbial communities. The study of Martian meteorites has provided detailed information about Martian geology, atmospheric composition, and potentially astrobiology. These rocks, blasted from Mars by asteroid impacts and eventually delivered to Earth, contain trapped atmospheric gases that match measurements from Mars landers and orbiters. Some meteorites show evidence for aqueous alteration that occurred on Mars, while others preserve igneous processes that reveal information about Martian interior composition. Recent discoveries of methane in the Martian atmosphere have generated significant scientific interest, because methane can be produced by both biological and geological processes. The methane appears to be released episodically from subsurface sources and is destroyed relatively quickly in the oxidizing Martian atmosphere. Understanding the source of this methane could provide important clues about current geological activity, or possibly even biological processes operating in Mars's subsurface. The evolution of Mars from a potentially habitable world to its current frozen state provides crucial insights into planetary habitability and the factors that determine whether Earth-like worlds can maintain stable climates over geological timescales. Mars demonstrates how planetary mass, magnetic field strength, and atmospheric loss processes can interact to transform habitable conditions into hostile environments. Comparative studies of Mars and Earth reveal the importance of planetary size in determining long-term habitability. Earth's larger mass enables it to retain substantial atmospheres and maintain active geological processes that help regulate climate, while Mars's smaller size led to rapid atmospheric loss and the cessation of major geological activity. These differences highlight the narrow range of planetary characteristics that may be necessary for sustaining habitable conditions over billions of years. Understanding Martian climate evolution also provides important context for interpreting observations of exoplanets, particularly super-Earths and mini-Neptunes that have no analogues in our solar system. The processes that led to Mars's atmospheric loss and climate change may operate differently on planets with intermediate masses between Earth and Neptune, affecting their potential for habitability around other stars. As we continue exploring Mars through robotic missions and eventual human exploration, this red world serves as a natural laboratory for understanding planetary formation, climate evolution, and astrobiology. Its accessible surface preserves a detailed record of early solar system conditions and the environmental changes that can transform potentially habitable worlds into the diverse planetary landscapes we observe throughout the universe. Between the orbits of Mars and Jupiter lies a region that tells one of the most fascinating stories of planetary formation, not of successful world-building, but of a process interrupted and frozen in time. The asteroid belt contains hundreds of thousands of rocky bodies, ranging from dust grains to objects hundreds of kilometers across, representing the preserved remnants of planetesimal formation from the earliest epochs of solar system history. These ancient fragments provide unparalleled insights into the materials, processes, and conditions that shaped terrestrial planet formation 4.5 billion years ago. The asteroid belt occupies the region from approximately 2.2 to 3.3 astronomical units from the Sun, a location where theoretical models initially predicted another terrestrial planet should have formed. The total mass of all asteroids combined amounts to only about 4% of our Moon's mass, far too little to have assembled into a planetary body. This mass deficit represents one of the fundamental puzzles of solar system architecture that can only be explained through the dynamical influence of nearby Jupiter. During the early phases of solar system formation, the region that now contains the asteroid belt likely possessed much more solid material than currently observed. Computer simulations suggest that the original mass of planetesimals in this region may have been comparable to Earth's mass, providing sufficient raw materials for terrestrial planet formation. However, gravitational perturbations from the rapidly growing Jupiter prevented efficient accretion, while gradually removing most of the original solid material through various dynamical processes. The mechanism responsible for truncating planetary formation in the asteroid belt involves orbital resonances with Jupiter. Objects in certain orbital periods experience periodic gravitational tugs from Jupiter that gradually increase their orbital eccentricities and inclinations. These enhanced orbital elements lead to more violent collisions between planetesimals and increase the probability that objects will be scattered into planet-crossing orbits, where they can be ejected from the solar system or impact other bodies. The Grand TAC model provides a comprehensive explanation for both the asteroid belt's current structure and Mars's small size. This model proposes that Jupiter migrated inward during the gas-rich phase of disk evolution, reaching an orbital distance as small as 1.5 astronomical units before reversing direction and migrating outward to its current position. This inward migration would have scattered planetesimals from the asteroid belt region throughout the inner solar system while preventing efficient planetary accretion in the Mars zone. Asteroid compositions reveal the temperature and chemical gradients that existed in the early solar nebula with remarkable precision. The innermost asteroids, located closest to the Sun, consist primarily of metal and silicate materials that could remain stable at high temperatures. Moving outward through the belt, asteroids show increasing abundances of hydrated minerals, organic compounds, and other materials that require cooler formation conditions. This compositional gradient preserves information about the condensation sequence that operated during solar nebula cooling. Close to the Sun, only the most refractory materials like metallic iron, nickel, and calcium aluminum inclusions could condense from the gas phase. At intermediate distances, silicate minerals became stable, while the outer regions of the asteroid belt reached temperatures cool enough for hydrated minerals and organic compounds to survive. The three major asteroid classes, S-type, C-type, and M-type, represent different stages of this condensation sequence and subsequent processing. S-type asteroids consist primarily of silicate minerals and appear to be the parent bodies of ordinary chondrite meteorites, the most common type of meteorite falling to Earth. Their spectra indicate compositions similar to the silicate mantles of differentiated planetesimals. C-type asteroids dominate the outer asteroid belt and contain high abundances of carbon compounds, hydrated minerals, and organic materials. These primitive bodies appear to have experienced minimal thermal processing since their formation, preserving pristine samples of the materials that accreted in the cooler regions of the early solar system. Some C-type asteroids may contain up to 20% water by mass, locked within hydrated mineral structures. M-type asteroids appear to represent the exposed metallic cores of differentiated planetesimals that lost their silicate mantles through catastrophic collisions. These objects provide direct samples of core materials that would otherwise be inaccessible in intact planetary bodies. The metallic composition of M-type asteroids matches that inferred for the cores of terrestrial planets, offering insights into the differentiation processes that separated metals from silicates during planetary formation. The asteroid belt also contains several objects large enough to have undergone significant geological processing during their formation. Ceres, the largest asteroid, with a diameter of approximately 950 kilometers, shows evidence for a differentiated interior with a rocky core, ice-rich mantle, and possibly subsurface liquid water. Vesta, the second largest asteroid, experienced extensive volcanism early in its history and possesses a basaltic crust similar to terrestrial volcanic rocks. The presence of these differentiated bodies indicates that some asteroids achieved sufficient size to undergo internal heating and melting despite the disruptive influence of Jupiter. Radioactive decay of short-lived isotopes, like aluminum-26, provided the energy source for melting, but only objects that accreted within the first few million years of solar system history could trap enough of these rapidly decaying isotopes to achieve melting temperatures. Asteroid families represent groups of objects with similar orbital characteristics and compositions that form through the catastrophic fragmentation of larger parent bodies. The identification of these families through statistical analysis of orbital elements reveals that the asteroid belt has experienced extensive collisional evolution throughout solar system history. Major collisional events have shattered large asteroids into numerous smaller fragments while excavating materials from different depths within differentiated parent bodies. The Kirkwood gaps in the asteroid belt represent regions of orbital space that are nearly empty due to orbital resonances with Jupiter. Objects in these resonant locations experience periodic gravitational perturbations that eventually remove them from stable orbits. The locations of these gaps correspond precisely to simple ratios of orbital periods with Jupiter, such as 3:1, 5:2, and 2:1 resonances. These resonant gaps demonstrate the ongoing dynamical evolution of the asteroid belt under Jupiter's gravitational influence. Objects scattered from resonant locations can evolve into Earth-crossing or Mars-crossing orbits, contributing to the population of potentially hazardous asteroids that pose impact threats to terrestrial planets. Understanding these dynamical pathways helps predict the long-term evolution of asteroid orbits and assess impact risks. The asteroid belt serves as the primary source of meteorites that fall to Earth, providing direct laboratory samples of early solar system materials. Different meteorite types originate from different asteroid classes and preserve information about various stages of planetesimal formation and evolution. Chondrite meteorites contain primitive materials that are accreted directly from the solar nebula, while achondrite meteorites come from differentiated asteroids that experienced melting and igneous processing. Carbonaceous chondrite meteorites, derived from C-type asteroids, contain the most primitive materials available for laboratory study. These meteorites preserve pre-solar grains that formed around other stars before the solar system existed, organic compounds that may have contributed to the origin of life on Earth, and refractory inclusions that condense directly from the solar nebula at temperatures exceeding 1,300 degrees Celsius. The study of meteorites has revolutionized our understanding of solar system chronology and the timescales of planetary formation processes. Radiometric dating of different meteorite components reveals that calcium-aluminum inclusions formed 4.567 billion years ago, providing the most precise age determination for solar system formation. Chondrules, spherical silicate objects found in primitive meteorites, formed over several million years through repeated melting events in the solar nebula. Water-bearing minerals in carbonaceous chondrites indicate that liquid water existed within asteroid parent bodies during the first few million years of solar system history. This aqueous alteration occurred when ice melted due to radioactive heating, creating environments where complex organic chemistry could occur. Some researchers propose that asteroids may have been important sites for prebiotic chemical evolution that eventually led to the origin of life. The asteroid belt also contains several objects with comet-like properties, blurring the traditional distinction between asteroids and comets. These main belt comets exhibit sublimation activity when solar heating releases volatile materials, despite being located in regions too warm for typical comet survival. Their existence suggests that the asteroid belt contains a reservoir of volatile materials that may have contributed to water delivery to the inner planets. Recent spacecraft missions to asteroids have revealed these objects to be much more complex and diverse than previously imagined. High-resolution imaging shows that many asteroids are contact binaries formed by the gentle collision and coalescence of two separate objects. Others exhibit evidence for mass wasting, thermal fracturing, and space weathering processes that continuously modify their surface properties. The presence of organic compounds on asteroid surfaces, confirmed by spectroscopic observations and meteorite analysis, demonstrates that complex carbon chemistry occurred throughout the early solar system. These materials may have been crucial for delivering the organic building blocks necessary for life to Earth and other terrestrial planets. Understanding the inventory and distribution of organic materials in asteroids helps constrain models for the origin of life. Future asteroid missions and sample return efforts will continue expanding our knowledge of these primitive objects and their role in planetary formation. The Japanese Hayabusa 2 mission and NASA's OSIRIS-REx mission have successfully returned samples from asteroids Ryugu and Bennu, respectively, providing pristine materials for detailed laboratory analysis. These samples will help answer fundamental questions about solar system formation, the origin of water and organic compounds, and the processes that shaped planetary compositions. As we continue studying the asteroid belt through observations, meteorite analysis, and spacecraft missions, these ancient remnants provide an irreplaceable archive of early solar system conditions. They preserve materials and processes that have been erased by geological activity on the planets, while revealing the complex interplay between dynamics, chemistry, and physics that shaped our cosmic neighborhood during its tumultuous youth. Understanding the asteroid belt helps us appreciate both the successful formation of planets and the fascinating alternatives that nature sometimes produces when planetary formation encounters unexpected obstacles. Jupiter represents the most influential member of our planetary family, a gas giant so massive that it contains more than twice the mass of all other planets combined. This colossal world fundamentally shaped the architecture of our entire solar system through gravitational interactions that controlled planet formation, scattered asteroids and comets, and continue to influence the orbits of smaller bodies throughout the outer solar system. Understanding Jupiter's formation and evolution reveals how giant planets can serve as both architects and guardians of planetary systems. The formation of Jupiter required conditions that existed only briefly during the early evolution of the solar nebula. Unlike terrestrial planets that formed primarily through collisional accretion of solid materials, gas giant formation demanded a two-stage process involving rapid core accretion, followed by massive atmospheric accumulation, before disk gas dissipation removed the raw materials for giant planet construction. The first stage of Jupiter's formation occurred through the same planetesimal accretion processes that built the terrestrial planets, but with a crucial advantage. Jupiter formed beyond the snow line where water ice could condense and remain stable. This additional ice component increased the solid surface density by approximately a factor of 4 compared to the inner solar system, providing abundant raw materials for rapid core growth. Computer simulations suggest that Jupiter's solid core reached a critical mass of approximately 10 to 15 Earth masses within the first few million years of solar system formation. Once a planetary embryo achieves this critical mass threshold, its gravitational field becomes strong enough to retain a substantial atmosphere of hydrogen and helium from the surrounding nebula gas. The transition from solid core growth to gas accretion represents a runaway process that can add hundreds of Earth masses of atmospheric material within a relatively short period. The runaway gas accretion phase proceeded through a process called core-powered accretion. As nebula gas fell onto the growing planet, gravitational compression heated the infalling material and established a hydrostatic atmosphere supported by thermal pressure gradients. The luminosity generated by continued solid accretion and atmospheric contraction drove convective mixing that enabled efficient heat transport and rapid atmospheric growth. Jupiter's formation had profound effects on the structure and evolution of the entire solar system through a process astronomers call the Grand Tax scenario. During the gas-rich phase of disk evolution, Jupiter experienced orbital migration through gravitational torques from the surrounding disk material. These torques initially caused Jupiter to spiral inward toward the Sun, potentially reaching orbital distances as small as 1.5 astronomical units. The inward migration of Jupiter would have catastrophically disrupted terrestrial planet formation by scattering planetesimals throughout the inner solar system and preventing efficient accretion in the Mars region. However, the subsequent formation of Saturn created a resonant configuration that reversed Jupiter's migration, causing both giant planets to move outward to approximately their current orbital positions. This outward migration scattered material from the inner solar system while allowing renewed terrestrial planet formation from the remaining debris. The timing and extent of Jupiter's migration fundamentally determined the final architecture of the inner solar system. Computer simulations show that without Jupiter's inward then outward migration, Mars would likely have grown to Earth-like proportions, while the asteroid belt would have accreted into another terrestrial planet. The actual occurrence of this migration explains both Mars's small size and the asteroid belt's current structure as a population of scattered remnants. Jupiter's massive gravitational field continues to influence solar system dynamics through its role as a cosmic vacuum cleaner that captures or deflects potentially hazardous comets and asteroids. Objects approaching the inner solar system from the outer regions often encounter Jupiter's gravitational sphere of influence, which can dramatically alter their trajectories. Some objects gain sufficient energy to be ejected from the solar system entirely, while others may be captured into stable or temporary orbits around Jupiter. The Shoemaker-Levy 9 impact in 1994 provided a dramatic demonstration of Jupiter's protective role when a fragmented comet collided with the giant planet's atmosphere. The energy released by these impacts exceeded the explosive power of the entire world's nuclear arsenal, illustrating the scale of destruction that such objects could cause if they impacted Earth instead of being intercepted by Jupiter. However, Jupiter's gravitational influence can also increase impact risks for inner solar system objects through a process called resonant pumping. Objects in certain orbital resonances with Jupiter experience periodic gravitational perturbations that can increase their orbital eccentricities and potentially send them on Earth-crossing trajectories. The asteroid belt contains several such resonant regions that serve as sources for potentially hazardous near-Earth asteroids. Jupiter's atmospheric composition provides important constraints on solar system formation models and the composition of the original solar nebula. The planet's atmosphere consists primarily of hydrogen and helium in proportions similar to the Sun, with trace amounts of methane, ammonia, water vapor, and other compounds. The abundances of heavy elements in Jupiter's atmosphere appear to be enriched compared to solar values, indicating that the planet accreted significant quantities of solid materials beyond what would be expected for simple gas capture. The deep atmospheric composition of Jupiter remains uncertain despite intensive study by the Juno spacecraft, which has been orbiting the planet since 2016. Measurements of water abundance have yielded conflicting results, with some regions showing higher concentrations than others. These variations may reflect complex atmospheric circulation patterns that mix materials from different depths and locations within Jupiter's massive envelope. Jupiter's internal structure likely consists of a solid core surrounded by distinct layers of metallic and molecular hydrogen. The core may contain between 7 and 25 Earth masses of rock and ice, though its exact composition and structure remain uncertain. Above the core, pressures exceed 4 million times Earth's atmospheric pressure, sufficient to transform hydrogen into a metallic state with electrical conductivity similar to metals. The metallic hydrogen region extends outward to approximately 60% of Jupiter's radius, where pressures decrease enough for hydrogen to exist in its normal molecular form. Convective motions within the metallic hydrogen layer, driven by heat transport from the interior, generate Jupiter's powerful magnetic field through dynamo processes. This magnetic field is approximately 20,000 times stronger than Earth's and creates an extensive magnetosphere that traps charged particles and generates intense radiation belts. Jupiter's magnetosphere represents the largest structure in the solar system, extending beyond the orbit of Saturn when the solar wind pressure is low. Charged particles trapped within this magnetosphere create hazardous radiation environments that pose significant challenges for spacecraft operations. The interaction between Jupiter's magnetic field and the solar wind also generates powerful radio emissions that can be detected by ground-based radio telescopes. The discovery of Jupiter's extensive moon system reveals the complex dynamics of satellite formation and evolution around giant planets. Jupiter possesses 4 large Galilean moons, Io, Europa, Ganymede and Callisto, that formed through processes analogous to planetary formation within a circumplanetary disk. These moons exhibit diverse geological characteristics ranging from active volcanism on Io to potential subsurface oceans on Europa and Ganymede. Io's extreme volcanic activity results from tidal heating generated by gravitational interactions with Jupiter and the other Galilean moons. The elliptical orbit induced by resonant interactions causes Io to experience varying tidal forces that flex and heat its interior, driving the most volcanically active body in the solar system. This tidal heating demonstrates how gravitational interactions can power geological activity even in the cold outer solar system. Europa's subsurface ocean represents one of the most promising locations for potential extraterrestrial life in our solar system. Tidal heating from Jupiter maintains liquid water beneath Europa's ice crust, creating an environment that may persist for billions of years. The interaction between this ocean and Europa's rocky interior could provide the chemical energy sources necessary to support life, making Europa a high-priority target for astrobiological exploration. Jupiter's irregular satellites, numbering in the dozens, represent captured asteroids and possibly comets that were gravitationally bound during encounters with the Jupiter system. These objects exhibit chaotic orbital characteristics, including high inclinations and eccentricities that distinguish them from the regular Galilean satellites. The capture and retention of irregular satellites demonstrates Jupiter's ability to gravitationally bind passing objects and may provide insights into early solar system dynamics. The study of Jupiter's atmospheric dynamics reveals complex circulation patterns driven by the planet's rapid rotation and internal heat source. Jupiter rotates once every 9 hours and 55 minutes, the fastest rotation of any planet in the solar system. This rapid rotation creates strong Coriolis forces that organize atmospheric flow into banded structures visible as alternating light and dark zones in telescopic observations. The Great Red Spot, a persistent anticyclonic storm system larger than Earth, has been observed continuously for more than 300 years. This enormous hurricane-like vortex is powered by Jupiter's internal heat and maintains its structure through interactions with surrounding atmospheric flows. Similar but smaller storm systems throughout Jupiter's atmosphere demonstrate the complex fluid dynamics operating in giant planet atmospheres. Jupiter radiates approximately 60% more energy than it receives from solar heating, indicating a substantial internal heat source. This excess energy likely results from gravitational contraction as the planet slowly shrinks under its own weight, converting gravitational potential energy into thermal energy. The time scale for this contraction spans billions of years, providing a long-term energy source that drives atmospheric circulation and supports geological activity on tidally heated satellites. Recent discoveries of numerous exoplanetary systems have revealed that Jupiter-like planets orbiting close to their parent stars, called hot Jupiters, are relatively common. These objects likely formed at distances comparable to Jupiter's current orbit, but subsequently migrated inward through gravitational interactions with their parent disks or other planets. The existence of hot Jupiters demonstrates that planetary migration can dramatically alter system architectures after formation. The specific orbital configuration of Jupiter and Saturn in our solar system may be crucial for maintaining Earth's habitability over geological timescales. The gravitational influence of these giant planets helps maintain stable orbits for the terrestrial planets, while preventing excessive bombardment by comets from the outer solar system. Changes in giant planet orbits could destabilize terrestrial planet orbits or increase impact rates to levels that would threaten complex life. Understanding Jupiter's formation and evolution provides crucial insights into the processes that govern giant planet formation throughout the universe. The requirements for rapid core accretion and gas capture before disk dispersal may make Jupiter-like planets relatively rare, as small changes in timing or disk properties could prevent successful giant planet formation. These constraints help explain the diversity of exoplanetary system architectures observed around other stars. As we continue studying Jupiter through ongoing spacecraft missions and theoretical modeling, this giant world serves as a natural laboratory for understanding atmospheric physics, magnetospheric processes, and satellite system dynamics. Its dominant role in shaping solar system architecture demonstrates how the formation of massive planets can influence the habitability and structure of entire planetary systems, making Jupiter not just our largest planetary neighbor, but also one of the most important factors determining the conditions that allowed life to emerge and flourish on Earth. Saturn represents one of nature's most spectacular achievements in planetary formation, a massive gas giant adorned with the most extensive and complex ring system in the solar system. This magnificent world, with a density so low it would float in water, demonstrates how subtle differences in formation conditions can create dramatically different outcomes, even among planets that formed through fundamentally similar processes. Saturn's unique characteristics and orbital evolution played crucial roles in shaping the final architecture of our planetary system. The formation of Saturn followed pathways similar to Jupiter, but with critical differences in timing and available materials that led to its distinctive characteristics. Like all giant planets, Saturn required rapid formation within the brief window where nebular gas remained available for atmospheric accretion. However, Saturn's greater distance from the Sun meant that solid materials were less abundant in its formation region, potentially slowing core assembly and affecting the final planetary characteristics. Saturn's core likely contains between 15 and 30 Earth masses of rock and ice, somewhat larger than Jupiter's core, despite Saturn's smaller total mass. This larger core fraction may result from Saturn's formation in a region of the solar nebula where ice comprised a larger fraction of the available solid materials. The enhanced ice abundance beyond Jupiter's orbit would have provided additional building blocks for core assembly, while reducing the time required to reach the critical mass threshold for gas accretion. The timing of Saturn's formation relative to Jupiter had profound consequences for both planets and the entire solar system. Computer simulations suggest that Saturn's core reached critical mass several million years after Jupiter began its runaway gas accretion phase. This delayed formation meant that Saturn accumulated its atmospheric envelope from gas that had already been partially depleted and heated by Jupiter's presence, resulting in Saturn's lower overall mass and density. The gravitational interaction between Jupiter and Saturn during their formation led to a complex dance of orbital migration that fundamentally shaped the solar system's final architecture. Initially, both planets migrated inward due to torques from the surrounding disk gas. However, when Saturn's mass became large enough to significantly affect disk dynamics, the two planets became trapped in a 2-to-1 orbital resonance that reversed their migration direction. This resonant configuration, sometimes called the Grand Tack scenario, caused both planets to migrate outward while maintaining their orbital period ratio. The outward migration scattered planetesimals from the inner solar system, truncating Mars's growth and creating the current asteroid belt structure. Without this resonant reversal, the inner solar system would likely have developed very different planetary masses and orbital configurations. Saturn's remarkably low density of just 0.69 grams per cubic centimeter results from its massive atmospheric envelope of hydrogen and helium surrounding a relatively modest solid core. The low density indicates that Saturn contains a higher fraction of light elements than Jupiter, consistent with formation in a region where volatile materials comprised a larger fraction of the available solid building blocks. The internal structure of Saturn likely consists of a solid core surrounded by a layer of liquid metallic hydrogen, above which lies an extensive envelope of molecular hydrogen and helium. The transition from molecular to metallic hydrogen occurs at lower pressures in Saturn than in Jupiter, due to Saturn's smaller mass and correspondingly lower internal pressures. This difference affects heat transport mechanisms and may explain some of the observed differences in atmospheric circulation between the two planets. Saturn generates its own internal heat source, radiating approximately 2.5 times more energy than it receives from solar heating. This excess energy likely results from gravitational contraction combined with helium differentiation, a process where helium droplets condense and fall through the lighter hydrogen envelope, releasing gravitational potential energy. This differentiation process may also explain observed differences in atmospheric helium abundance between Saturn and Jupiter. The atmospheric circulation on Saturn exhibits banded structure similar to Jupiter, but with some distinctive characteristics. Saturn's lower gravity and internal heat source create different conditions for atmospheric dynamics, resulting in broader zones and belts compared to Jupiter. The planet's rapid rotation period of 10 hours and 39 minutes generates strong Coriolis effects that organize atmospheric flow into longitudinal bands with alternating wind directions. Saturn occasionally develops massive storm systems that can span significant fractions of the planet's circumference. These great white spot storms appear roughly every 30 Earth years, corresponding to Saturn's orbital period around the Sun. The periodic nature of these storms may be related to seasonal variations in solar heating or internal dynamical processes that operate on Saturn's orbital timescale. Saturn's magnetic field, while much weaker than Jupiter's, exhibits the unusual characteristic of being nearly perfectly aligned with the planet's rotational axis. This alignment is puzzling because most planetary magnetic fields show significant tilts relative to rotation axes. The near-perfect alignment may indicate that Saturn's magnetic field generation process differs from the dynamo mechanisms operating in other planets. The magnetosphere of Saturn extends several times the planet's radius and interacts strongly with its extensive moon system and ring structure. Charged particles trapped within the magnetosphere create radiation belts, though these are much less intense than Jupiter's due to Saturn's weaker magnetic field. The interaction between the magnetosphere and Saturn's moons creates complex plasma dynamics that affect both the satellites and the ring system. Saturn's moon system reveals diverse formation and evolutionary processes operating in the outer solar system. Titan, Saturn's largest moon, possesses a thick nitrogen atmosphere and surface lakes of liquid methane and ethane, creating the most Earth-like surface environment found anywhere else in the solar system. The presence of liquid on Titan's surface demonstrates that complex hydrological cycles can operate using compounds other than water under appropriate temperature and pressure conditions. Enceladus, one of Saturn's smaller moons, exhibits active water-ice volcanism through geysers that eject material from its south polar region. These geysers indicate the presence of a subsurface liquid water ocean beneath Enceladus's ice crust, maintained by tidal heating from orbital resonances with other Saturn moons. The discovery of organic compounds and hydrothermal activity associated with this subsurface ocean makes Enceladus another high-priority target for astrobiological research. The orbital resonances among Saturn's moons demonstrate the complex gravitational interactions that can develop in satellite systems over geological timescales. Many of Saturn's moons participate in resonant chains where orbital periods maintain simple integer ratios, indicating that these systems have evolved through tidal interactions and gravitational capture into stable configurations. Saturn's ring system represents the most extensive and dynamically complex ring structure in the solar system, consisting of countless particles ranging in size from dust grains to house-sized boulders. The rings exhibit intricate structure, including gaps, spokes, braided segments, and shepherding satellites that demonstrate the complex interplay between gravitational forces, collisional processes, and electromagnetic effects. The origin of Saturn's rings remains debated, with proposed mechanisms including the disruption of a large moon that approached within Saturn's Roche limit, the collision of existing moons, or the capture and disruption of a passing comet or asteroid. Age estimates for the rings range from very young, less than 100 million years, to as old as the solar system itself, depending on assumed evolutionary rates and composition. The ring particles consist primarily of water ice with varying amounts of rocky contamination. Spectroscopic observations reveal compositional variations both radially and azimuthally within the ring system, indicating complex evolutionary processes involving particle collisions, electromagnetic forces, and gravitational interactions with nearby moons. The ring system serves as a natural laboratory for studying many-body gravitational dynamics and collisional processes. Ring dynamics involve numerous physical processes, including gravitational perturbations from Saturn's moons, collisional evolution of ring particles, electromagnetic effects involving charged dust grains, and radiation pressure from solar photons. These processes operate on timescales ranging from orbital periods of hours to evolutionary timescales of millions or billions of years, creating the complex structures observed in high-resolution spacecraft images. The Cassini-Huygens mission, which operated in the Saturn system from 2004 to 2017, revolutionized our understanding of Saturn, its rings, and its moons. The mission revealed previously unknown ring structures, discovered new moons, characterized the composition and dynamics of Titan's atmosphere, and detected active geology on multiple satellites. The mission's grand finale involved multiple passes through the gap between Saturn and its innermost rings, providing unprecedented measurements of Saturn's interior structure and ring composition. Recent analysis of Cassini data has provided new constraints on Saturn's internal structure and formation history. Measurements of Saturn's gravitational field reveal that the planet's core is larger and more diffuse than previously thought, possibly indicating incomplete separation of rock and ice during formation or subsequent mixing due to convective motions. These findings challenge traditional models of giant planet internal structure and evolution. The study of Saturn's orbital evolution provides important insights into the early dynamical history of the outer solar system. The late heavy bombardment period, which affected the inner solar system approximately 4 billion years ago, may have been triggered by instabilities in the orbits of the giant planets, including Saturn. Computer simulations suggest that gravitational interactions between the giant planets could have scattered populations of asteroids and comets throughout the solar system. Saturn's influence on small body populations continues today through gravitational perturbations that affect comet orbits and asteroid trajectories. Objects in the Kuiper belt and scattered disk regions can be perturbed by Saturn's gravity into orbits that bring them into the inner solar system as long-period comets. Understanding these dynamical pathways helps predict the long-term evolution of small body populations and potential impact hazards. The discovery of numerous exoplanetary systems has revealed that Saturn-mass planets are relatively common around other stars, though many orbit much closer to their parent stars than Saturn orbits the Sun. These hot Saturns likely formed at distances similar to Saturn's current orbit, but migrated inward through gravitational interactions with their parent disks or other planets. The diversity of exoplanetary system architectures demonstrates that planetary migration can create very different outcomes from similar initial conditions. Understanding Saturn's formation and evolution provides crucial insights into the processes that govern giant planet formation and the factors that determine the final architecture of planetary systems. The specific orbital relationship between Jupiter and Saturn in our solar system may be necessary for maintaining the stable, habitable conditions that exist on Earth. Changes in giant planet orbits or masses could destabilize terrestrial planet orbits and affect the delivery of volatile materials necessary for life. As we continue studying Saturn through ongoing analysis of Cassini data and future missions, this magnificent ringed world serves as a natural laboratory for understanding atmospheric dynamics, magnetospheric physics, ring dynamics, and satellite evolution. Its unique characteristics and evolutionary history demonstrate how subtle differences in formation conditions can create dramatically different planetary outcomes, while highlighting the complex gravitational interactions that shaped our entire solar system's architecture. Uranus presents one of the most enigmatic and unusual worlds in our solar system, an ice giant that rolls along its orbital path like a cosmic bowling ball rather than spinning upright like other planets. This strange orientation, with an axial tilt of 98 degrees that places its rotational axis nearly in the plane of its orbit, provides compelling evidence for a catastrophic collision that fundamentally altered the planet's characteristics during the early epochs of solar system formation. The formation of Uranus occurred in the frigid outer reaches of the solar nebula, approximately 19 astronomical units from the Sun, where temperatures were cold enough for water, methane and ammonia to condense into solid ices. These volatile materials, combined with rocky and metallic components, provided the building blocks for ice giant formation through processes that differed significantly from the gas giant formation mechanisms that created Jupiter and Saturn. Unlike the gas giants, which consist primarily of hydrogen and helium captured from the solar nebula, ice giants like Uranus contain much larger fractions of heavier materials, including water, methane, ammonia, and rocky components. This compositional difference reflects both the lower abundances of hydrogen and helium in the outer solar nebula and the longer timescales required for planetary growth at such large distances from the Sun. The core accretion model for ice giant formation suggests that Uranus began as a solid planetary embryo that accumulated ice and rock through planetesimal collisions over millions of years. However, by the time this core reached sufficient mass to begin capturing substantial amounts of hydrogen and helium from the surrounding nebula, most of the disk gas had already dissipated. This timing constraint explains why ice giants possess much smaller atmospheric envelopes relative to their solid components compared to the gas giants. Uranus likely contains a core of rock and metal, surrounded by a mantle of water, methane and ammonia in various phases, topped by a relatively thin atmosphere of hydrogen and helium, with traces of methane that give the planet its distinctive blue-green color. The mass distribution within Uranus differs dramatically from Jupiter and Saturn, with the majority of the planet's mass contained in solid and liquid phases rather than gaseous hydrogen and helium. The most striking characteristic of Uranus is its extreme axial tilt that causes the planet to rotate on its side relative to its orbital motion. This unusual orientation creates extraordinary seasonal variations, where each pole experiences 42 years of continuous sunlight followed by 42 years of darkness as Uranus completes its 84-year orbit around the Sun. No gradual evolutionary process could have produced such an extreme tilt, strongly suggesting that Uranus experienced a catastrophic collision early in its history. computer simulations of giant impacts on forming planets reveal that a collision with an Earth-sized or larger impactor could have tilted Uranus to its current orientation while preserving the planet's basic structure and satellite system. Such an impact would need to have occurred during the final stages of planetary formation, when Uranus had achieved most of its current mass, but before its satellite system had fully stabilized. The timing and characteristics of this hypothetical giant impact provide important constraints on the early dynamical evolution of the outer solar system. The impacting body may have been a planetary embryo that was scattered from its original formation location by gravitational interactions with the migrating giant planets. Such scattering events were likely common during the period of planetary migration that followed the initial formation of Jupiter and Saturn. Alternative models propose that Uranus's unusual tilt resulted from resonant interactions during planetary migration rather than a single catastrophic collision. In this scenario, gravitational perturbations from other giant planets could have driven Uranus through spin-orbit resonances that gradually increased its obliquity to the observed extreme value. However, most dynamical models favor the giant impact hypothesis as the most plausible explanation for such a large axial tilt. The atmospheric composition of Uranus provides important clues about ice giant formation processes and the volatile inventory of the outer solar nebula. Methane comprises approximately 2% of the atmospheric mass and is responsible for the planet's distinctive coloration through selective absorption of red wavelengths of sunlight. The abundance of methane and other trace constituents reflects the composition of ices that condensed in the formation region of ice giants. Uranus exhibits much less atmospheric activity than the gas giants, with wind speeds and storm systems that are relatively modest compared to the dynamic atmospheres of Jupiter and Saturn. This reduced activity may result from Uranus's unusual seasonal heating pattern, which creates very different thermal gradients compared to planets with more typical axial tilts. The planet's internal heat source is also much weaker than those of other giant planets, providing less energy to drive atmospheric circulation. Recent observations have revealed that Uranus does experience seasonal atmospheric changes, as different regions of the planet receive varying amounts of solar heating throughout its long orbital period. Cloud features and atmospheric banding become more prominent as regions emerge from decades of darkness into sunlight. These observations provide insights into atmospheric dynamics under extreme seasonal conditions that have no analogue elsewhere in the solar system. The magnetic field of Uranus exhibits another highly unusual characteristic. It is tilted approximately 60 degrees relative to the planet's rotational axis and offset from the planetary center by approximately 1/3 of Uranus's radius. This geometry differs dramatically from the magnetic fields of other planets and suggests that the field generation mechanism in ice giants may be fundamentally different from the dynamo processes operating in terrestrial planets and gas giants. The unusual magnetic field geometry may result from the magnetic field being generated in a thin shell of convecting water and ammonia rather than in a central metallic core. High-pressure experiments suggest that water can become electrically conductive under the pressure and temperature conditions that exist in Uranus's interior, potentially enabling dynamo action in regions that would not conduct electricity under normal conditions. The discovery that both Uranus and Neptune possess similarly tilted and offset magnetic fields suggests that this characteristic may be common to ice giants rather than resulting from the specific impact that tilted Uranus. This similarity supports models where magnetic field generation occurs in conducting fluid layers rather than solid metallic cores, representing a distinct type of planetary dynamo mechanism. Uranus possesses a complex ring system that was discovered through stellar occultation observations in 1977. The rings consist primarily of dark, narrow bands of material that are much less prominent than Saturn's extensive ring system, but more dynamically complex than the simple ring systems of Jupiter and Neptune. The ring particles appear to be composed of organic compounds or radiation-darkened materials rather than the bright water ice that dominates Saturn's rings. The narrow width and sharp edges of Uranus's rings indicate that they are confined by gravitational interactions with small shepherd satellites, similar to mechanisms operating in Saturn's ring system. However, the specific dynamics of ring confinement around Uranus remain poorly understood due to limited observational data from the single Voyager 2 flyby in 1986. The satellite system of Uranus includes 5 major moons: Miranda, Ariel, Umbriel, Titania and Oberon, that orbit in the planet's equatorial plane, confirming that they formed after the giant impact that tilted the planet. These moons exhibit diverse geological characteristics ranging from Miranda's bizarre patchwork terrain to evidence for past geological activity on several of the larger satellites. Miranda, the smallest and innermost of Uranus's major moons, displays some of the most spectacular and puzzling geology found anywhere in the solar system. The satellite's surface consists of distinct terrain types, including heavily cratered regions, grooved plains, and massive cliff structures that suggest episodes of intense geological activity despite Miranda's small size and presumably cold interior. The origin of Miranda's unusual surface features remains controversial, with proposed explanations including tidal heating from orbital resonances, differentiation, and convective overturn within the satellite's interior, or catastrophic disruption and reassembly following a major collision. Each hypothesis faces significant challenges in explaining the observed geological relationships and the timing of surface formation. The larger Uranian satellites show evidence for past geological activity, including tectonic features, possible cryovolcanic deposits, and compositional variations that indicate internal differentiation. However, the limited resolution and coverage of Voyager 2 images leave many questions about the geological evolution of these distant worlds unanswered. Recent ground-based and space-based observations have revealed additional small satellites of Uranus, bringing the total known satellite count to 27. Many of these newly discovered objects are small, irregular satellites that likely represent captured asteroids or comets rather than objects that formed with Uranus through accretion processes in a circumplanetary disk. The discovery of irregular satellites around all giant planets suggests that satellite capture was a common process during the early evolution of the outer solar system. The capture mechanisms likely involved gravitational interactions during close encounters with passing objects, possibly enhanced by gas drag during the period when circumplanetary disks were present around the forming giant planets. The study of Uranus provides important insights into ice giant formation processes and the range of outcomes possible during planetary formation in the outer solar system. The compositional differences between ice giants and gas giants reflect the varying conditions and material inventories present at different distances from the Sun during nebular evolution. Understanding ice giant formation also provides crucial context for interpreting observations of exoplanets, as Neptune-sized worlds appear to be among the most common types of planets discovered around other stars. Many of these exoplanets orbit much closer to their parent stars than Uranus orbits the Sun, suggesting that planetary migration can transport ice giants from their formation locations to very different orbital environments. The atmospheric composition and structure of ice giants like Uranus provide natural laboratories for studying the behavior of materials under extreme pressure and temperature conditions that cannot be replicated in terrestrial laboratories. The physics of superionic water, metallic hydrogen and other exotic phases of matter that may exist in ice giant interiors has implications for understanding planetary formation, evolution and habitability. The seasonal variations on Uranus offer unique opportunities to study atmospheric dynamics under extreme conditions that provide tests for theoretical models of planetary atmospheres. The 42-year cycles of heating and cooling create natural experiments in atmospheric response to changing energy inputs that may have applications to understanding climate systems on other worlds. Future missions to the ice giants represent high-priority objectives for planetary science, as these distant worlds remain among the least explored objects in our solar system. Only a single spacecraft, Voyager 2, has visited Uranus, providing just a brief snapshot of the planet's characteristics during a single season. Dedicated orbiter missions could revolutionize our understanding of ice giant atmospheres, interiors, magnetospheres, rings and satellite systems. The unique characteristics of Uranus serve as a reminder that planetary formation can produce outcomes that challenge our expectations and require explanation through catastrophic events rather than gradual evolutionary processes. The giant impact that tilted Uranus demonstrates the chaotic and violent nature of early solar system evolution, while highlighting how collisional processes shape the final characteristics of planetary bodies throughout our cosmic neighborhood. As we continue studying Uranus through ground-based observations, theoretical modeling and planning for future space missions, this sideways world provides essential insights into the formation and evolution of ice giants throughout the universe. Its unusual characteristics preserve evidence for the dynamic processes that operated during the solar system's youth, while demonstrating the remarkable diversity of outcomes possible through planetary formation processes. Neptune holds the distinction of being the first planet discovered through mathematical prediction rather than direct observation, representing one of the greatest triumphs of theoretical astronomy and our understanding of gravitational physics. This distant ice giant, located 30 times farther from the Sun than Earth, reveals the precision with which Newton's law of universal gravitation describes planetary motions, while demonstrating how subtle gravitational perturbations can lead to extraordinary scientific discoveries. The story of Neptune's discovery begins with unexplained irregularities in the orbit of Uranus that became apparent as astronomers accumulated decades of positional measurements following William Herschel's discovery of the seventh planet in 1781. By the early 19th century, careful analysis revealed that Uranus was not following the elliptical path predicted by Newton's laws, when only the gravitational influences of the Sun and known planets were considered. These orbital deviations, though small, were systematic and persistent, suggesting the presence of an additional gravitational influence rather than observational errors or inadequacies in Newton's theory. The discrepancies amounted to only a few arc-seconds in Uranus's position, but such precision was achievable by the most skilled observers of the era, using high-quality telescopes and careful measurement techniques. Two mathematicians working independently, Urbain Le Verrier in France and John Couch Adams in England, tackled the formidable challenge of determining the location of the hypothetical perturbing planet based solely on its gravitational effects on Uranus. This inverse problem required solving complex equations involving the interactions of multiple massive bodies over decades of orbital motion. Le Verrier's calculations, completed in 1846, predicted that an unknown planet should be located at a specific position in the constellation Aquarius. When German astronomer Johann Galle searched this predicted location using the Berlin Observatory's excellent star charts, he found Neptune within 1 degree of Le Verrier's calculated position on the first night of searching. This remarkable confirmation validated both Newton's law of gravitation and the power of mathematical analysis to reveal hidden aspects of the natural world. Neptune's discovery demonstrated that gravitational interactions could be used as tools for exploring the solar system, establishing precedents for later discoveries of Pluto, numerous asteroids, and eventually exoplanets around other stars. The success of this gravitational detective work encouraged astronomers to look for similar perturbations that might reveal additional unknown worlds. The formation of Neptune occurred in the distant reaches of the solar nebula, where temperatures were cold enough for volatile materials including water, methane, and ammonia to condense into solid ices. Like Uranus, Neptune represents an ice giant with a composition dominated by water, rock, and ices, rather than the hydrogen and helium that comprise the gas giants Jupiter and Saturn. Neptune likely formed through core accretion processes, similar to those that created Uranus, beginning as a solid planetary embryo that accumulated ice and rock through planetesimal collisions over millions of years. However, Neptune's greater distance from the Sun meant that growth rates were slower due to lower solid surface densities and longer orbital periods that reduced collision frequencies between planetesimals. The ice giant formation process required careful timing to capture even modest atmospheric envelopes of hydrogen and helium before nebula gas dissipated. Computer models suggest that Neptune's core reached critical mass for gas capture near the end of the nebula lifetime, resulting in a relatively thin atmospheric envelope compared to the massive gaseous envelopes of Jupiter and Saturn. Neptune's internal structure likely consists of a rocky core surrounded by a mantle of water, methane and ammonia in various phases, topped by an atmosphere containing hydrogen, helium and methane. The planet's deep blue color results from methane absorption of red wavelengths, similar to Uranus but more pronounced due to higher methane concentrations in Neptune's atmosphere. Despite receiving only 1/1000th the solar energy that Earth receives, Neptune exhibits remarkably dynamic atmospheric activity with wind speeds exceeding 2,000 kilometers per hour, the fastest recorded in the solar system. This extreme atmospheric activity puzzles planetary scientists because the energy available from solar heating alone seems insufficient to drive such vigorous circulation patterns. The source of energy driving Neptune's atmospheric dynamics likely includes substantial internal heat generation, as Neptune radiates approximately 2.6 times more energy than it receives from the Sun. This internal heat source may result from gravitational contraction, radioactive decay, or possibly differentiation processes involving the settling of heavier materials toward the planet's center. Neptune's magnetic field exhibits characteristics similar to Uranus, with a significant tilt relative to the planet's rotational axis and an offset from the planetary center. This similarity suggests that both ice giants generate their magnetic fields through dynamo processes operating in conducting fluid layers, rather than metallic cores, representing a distinct type of planetary magnetism. The magnetic field geometry indicates that field generation occurs in a shell of convecting water and ammonia at intermediate depths within Neptune's interior. Laboratory experiments demonstrate that water can become electrically conductive under the extreme pressure and temperature conditions present in ice giant interiors, enabling dynamo action in regions that would be insulators under normal conditions. Neptune's largest moon, Triton, represents one of the most fascinating objects in the outer solar system and provides crucial insights into the early dynamical evolution of the Kuiper Belt region. Triton orbits Neptune in a retrograde direction, indicating that it was not formed through accretion in a circumplanetary disk, but rather represents a captured Kuiper Belt object that was gravitationally bound during a close encounter with Neptune. Triton's capture likely occurred through a three-body interaction involving Triton, Neptune, and a companion object that was ejected from the system while Triton became gravitationally bound. This process would have initially placed Triton in a highly elliptical orbit that gradually circularized through tidal interactions with Neptune over millions of years. The surface of Triton exhibits evidence for geological activity, including nitrogen geysers, smooth plains that may represent cryovolcanic flows, and a thin atmosphere composed primarily of nitrogen with traces of methane. Despite surface temperatures of -235 degrees Celsius, Triton shows signs of ongoing geological processes powered by tidal heating and radioactive decay. Triton's retrograde orbit causes it to gradually spiral inward toward Neptune due to tidal friction, a process that will eventually bring the Moon within Neptune's Roche limit, where it will be disrupted and form a spectacular ring system. This fate awaits Triton in approximately 3.5 billion years, demonstrating how satellite systems can evolve dramatically over geological timescales. The capture of Triton likely disrupted any regular satellite system that may have existed around Neptune during its formation. Computer simulations suggest that the gravitational perturbations associated with Triton's capture and orbital evolution would have destabilized the orbits of any pre-existing regular satellites, either causing them to collide with Neptune or escape from the system entirely. Neptune possesses several small, irregular moons that likely represent additional captured Kuiper Belt objects or fragments produced during Triton's capture event. These objects exhibit diverse orbital characteristics, including high inclinations and eccentricities that distinguish them from regular satellites formed through accretion processes. Recent discoveries have expanded Neptune's known satellite system to 14 objects, though most of these are small, irregular bodies discovered through careful surveys using large ground-based telescopes. The properties of these irregular satellites provide insights into the population of small bodies that existed in the outer solar system during Neptune's formation and early evolution. Neptune also possesses a ring system consisting of several narrow, discontinuous arcs rather than complete rings. These ring arcs appear to be confined by gravitational interactions with small shepherd satellites, similar to mechanisms operating in other planetary ring systems. The ring material consists of dark particles, possibly organic compounds or radiation-processed ices. The discovery and characterization of Neptune's rings required advanced observational techniques including stellar occultations and high-resolution imaging from spacecraft. The ring system was first detected through occultation observations that revealed periodic dimming of background stars, indicating the presence of narrow bands of orbiting particles. The Voyager 2 spacecraft, which flew past Neptune in 1989, provided the only close-up observations of the Neptune system to date. This encounter revealed the complex atmospheric dynamics, magnetic field characteristics, and detailed properties of Triton that form the basis of our current understanding of the Neptune system. Voyager 2's observations of Neptune's atmosphere revealed large-scale storm systems, including the Great Dark Spot, a hurricane-like feature comparable in size to Jupiter's Great Red Spot. However, subsequent observations by the Hubble Space Telescope showed that this feature had disappeared, indicating that Neptune's atmospheric dynamics operate on much shorter timescales than the persistent features observed on Jupiter. The rapid changes in Neptune's atmospheric features demonstrate the dynamic nature of weather patterns on ice giant planets and provide insights into atmospheric physics under extreme conditions. The energy sources driving such vigorous atmospheric activity despite minimal solar heating remain active areas of research in planetary science. Neptune's orbital characteristics preserve information about the early dynamical evolution of the outer solar system. The planet's nearly circular orbit and moderate eccentricity suggest that it has remained relatively stable since achieving its current orbital configuration, unlike scenarios involving dramatic orbital migration or gravitational scattering. However, theoretical models of outer solar system evolution suggest that Neptune may have formed closer to the Sun and subsequently migrated outward to its current location. This migration would have occurred through gravitational interactions with planetesimals and disk material during the final stages of solar system formation. The NICE model of outer solar system evolution proposes that gravitational instabilities among the giant planets cause Neptune to migrate outward while scattering populations of small bodies throughout the outer solar system. This migration may have triggered the late heavy bombardment period that affected the inner solar system approximately 4 billion years ago. Neptune's gravitational influence continues to shape the architecture of the outer solar system through its interactions with Kuiper belt objects and other small bodies. Objects in orbital resonances with Neptune, including Pluto, maintain stable orbital configurations despite the planet's strong gravitational perturbations. The study of Neptune provides crucial insights into ice giant formation processes and the factors that determine planetary characteristics in the outer regions of planetary systems. Understanding Neptune's formation, structure and evolution helps interpret observations of similar-sized exoplanets, which appear to be among the most common types of planets around other stars. Neptune serves as a natural laboratory for studying atmospheric dynamics, magnetospheric physics, and satellite evolution under extreme conditions that cannot be replicated in terrestrial environments. Its distant location and extreme seasonal variations provide unique opportunities to test theoretical models of planetary atmospheres and climate systems. Future exploration of Neptune represents a high priority for planetary science, as this distant world remains among the least studied planets in our solar system. Advanced propulsion technologies and innovative mission designs could enable detailed studies of Neptune's atmosphere, interior structure, magnetic field, and satellite system that would revolutionize our understanding of ice giant planets. The discovery of Neptune through mathematical analysis stands as one of the greatest achievements in theoretical astronomy and demonstrates the power of scientific prediction based on fundamental physical laws. This triumph of human intellect over observational limitations continues to inspire scientists seeking to understand the hidden workings of the natural world through careful analysis and mathematical insight. As we continue studying Neptune through ground-based observations, theoretical modeling, and planning for future space missions, this distant blue giant provides essential insights into planetary formation processes, atmospheric physics, and the dynamical evolution of planetary systems. Its unique characteristics and evolutionary history contribute to our understanding of the diverse outcomes possible through planetary formation, while highlighting the continuing mysteries that await discovery in the outer reaches of our solar system.